कॉफ़ी नहीं लिया? कॉफ़ी नहीं लिया?
इधर चलो, लाइव देख रखे हैं।
कहाँ लग गया ना क्या?
यहाँ ना एक बॉटल रखना पड़ेगा।
एक तो है, एक खाली उधर खत्म हुआ, ये देखिए वही लोग बैठे हैं ना, दूसरा चेंज हो गया।
अभी ये सर लोग का ना ये वाला अलग अलग करके रखना पड़ेगा।
फिर अगेन बैठी हैं क्या?
अगेन कोई नहीं बैठेगा, वो अगेन यहाँ से आएगा और यहाँ पे मगर ये जैसे ये बनना सकता है तो ये बात तो उनको बैग करके देना पड़ेगा। प्रेम ये सब बाद में उनको बुक के ये जो है ना लिमिट है, लिमिटेड बैंक से बड़ा है उसको सबसे ये वाला सर उनको देना है। ये डायरेक्ट उसको दे देना तो डायरेक्ट बाकी मगर ये है कि अगर देना नहीं लेंगे अलग बात है। ये हमको जितना लगता है मगर ये अगर नहीं करते कि अगर है ना नहीं है तो इन लोग दोनों तरह के हम लोगों को देना चाहिए कैसे भी जस्ट हाँ सर रहेंगे दे विल बी हियर
मन्ना सर रहेगा, फिर रहेगा, फिर भी ठीक है, ठीक है।
ये दोनों का है।
नहीं नहीं ठीक, इधर रखिए, इधर तो कोई नहीं बैठेगा।
ये वाला हाँ
हाँ
No, no, it is with me. Yes, yes, I'm just giving.
Hello.
I'll bring it now.
Those who have finished your tea, please move inside. We are going to start our first lecture session.
हेलो हाँ हाँ आइए आइए
I request all the faculties and students in the auditorium foyer to please take your seat inside the auditorium. We are running short of time, and I request all of them to please come inside the auditorium. We are going to start our lecture session. Okay. Keep on coming. So welcome you all back. Now we are moving into the lecture session of this academia event. So it is my privilege to introduce our first speaker of this lecture session, Professor Sayan Bhattacharya of CSIR Kolkata. Professor Sayan Bhattacharya have completed his BS at University of Calcutta, MSc at University of Kalyani, and he completed his doctoral studies at the Indian Institute of Technology, Kanpur. Further, he carried out his postdoctoral research studies at Bar Ilan University, Israel, and Drexel Nanotechnology Institute, USA. In the year 2010, he joined as assistant professor at CSIR Kolkata. At present, he is in the capacity of professor at CSIR Kolkata. During the year 2016 and 20, he is the founder chair for the Center for Advanced Functional Materials established at CSIR Kolkata. His broad research interest includes photovoltaics and optoelectronics with metal halide perovskite nanostructures, electrochemical hydrogen fuel and CO2 detection, metal air battery, photo rechargeable battery. He has number of awards and credits on his name. He is a life fellow of Indian Chemical Society. He have various international awards and recognitions. Few of them are: he is an emerging investigator acknowledged by Journal of Material Chemistry A. He is in the editorial advisory board member of ACS Applied Energy Materials. He is the editor of Indian Journal of Chemistry, and he has been recognized with the SCRB Star Award. With these few words of introduction, I request Dr. Sayan Bhattacharya to hold this lecture. Yeah. Yeah.
Good. Pointer.
This is a pointer. You can check it.
Oh, yeah. Okay. Thank you. Thank you for this nice introduction, and I thank the organizers, Dr. Singh, Dr. Panda, Dr. Rev, and the fellow colleagues here for actually inviting me here for this 1 week, 1 lab, the CSR the program. So I was asked to give a lecture on the energy materials, so I changed the title a bit. So it is basically these energy solutions that we should see for the 21st century here. So this entire this G file that I put here, you can see that over a span of 100 years, how the the temperature of the earth is going up, and it is not actually uniform. At various places you see that the this temperature is going up by around 8 degrees. So it is actually this over 100 years, so we do not actually feel it. Okay, sometimes we actually talk about it. It is not like the COVID or it's not the cancer that we really see the problem, but it is a the persistent problem that we all need to solve. Okay, that is the one of the major big problems of this time. So I think where I should point it? Ah, okay. No, okay. No, pointer. I have to change the slide. Ah, yeah. Yeah. So the main problem is that we have the carbon dioxide and we need to reduce it. So we burn the fossil fuels, we know, and we have to come out of it. Okay, CO2, carbon dioxide, we emit it from every use. We actually the human beings or any of the animals, we breathe out this carbon dioxide. We inhale this oxygen and we take out this. So every industry, every furnace, everything takes out the carbon dioxide. What happens here, that we have many different gases in our atmosphere, but carbon dioxide is a heavy gas. It doesn't go up much into the air. So when we have this carbon dioxide, when the sun's light comes, this infrared radiation, the carbon dioxide will absorb, okay, and the molecules will vibrate like this, and then it will not allow this infrared to actually go out, rather it will give it back to the earth. So overall it will heat up the earth. So the main thing is that we have to reduce the emission of carbon dioxide from every possible application. Okay, that is the main thing, and that is all about the energy research that we talk about. We talk about solar cells, we talk about these electric vehicles, we talk about everything. It is about to minimize this carbon dioxide so that we do not allow the Earth's temperature to go up. That is the whole thing. Okay, now, so we have to make use of the renewable energy. So there are various types of renewable energy. You can see biomass, solar, wind, geothermal, water. Professor Manna has already said a lot beautifully over a wide spectrum of all this. I will basically focus on these three parts. I will tell you about the photovoltaics, the batteries, and the catalyst for the electrolyzer and the fuel cells. And these three things are actually we use in every corner of the world, in every application in our everyday life. Okay, so that is what I am going to tell you. So I will take up one by one these three and finish it in 30 minutes. So solar cells, and so solar cells, what they do, they convert the solar energy into the electrical energy. And believe me, all these numbers, these are these are given in TW, means the terawatt. So here, the amount of sun's energy that comes to the earth in the whole year, we use only 0.01%. Can you just imagine 0.01%? Rest 99.99 is totally lost. We don't actually use it. So we have to use this solar energy. Okay, so when we want to use the solar energy, what we think, okay, we have to make the solar cells, and if you have in your institute also, you will have a lot of these solar panels on top of your, the rooftops and everywhere. Now we want it to be a very green process. The green process means where the carbon footprint is minimal. It is not there, right? So what we use here right now, we use the silicon solar cells. I think all of you know it is the silicon solar cells. So silicon solar cells, when we use, but making those panels, the solar panels, do you think it is green? It is not green. It is absolutely not good process. So here is an article which says about the true carbon footprint of photovoltaic energy. Now here what I am going to tell you is all these reactions that you see. What happens? We have the silica, glass or sand, everything contains silica, SiO2, you react with the carbon at a very high temperature greater than 1500 degrees centigrade, you end up with silicon carbide. And then over a range of all these the reactions, it converts to the silicon. Now when it converts to the silicon, that's not end of it. You have to polish the surface of this silicon. You have to use strong acids. Okay? The whole process is such that every solar panel that you make, you emit 4 kg of carbon dioxide. Okay? So the process is not a green process. Even if you think that, okay, I am not plugging into the DC supply, I am taking it from the solar panel, but that's not true. You are also doing it, but it is up to us to solve this. So solution to this is we have to go for other types of solar cells. Now other types of solar cells, let me tell you about this is the generation 1. The first generation is based on this silicon wafers. You can see that the cost is pretty high, but this efficiency is actually limited. This efficiency means how much is the input power that is coming from the sun and how much electricity we are getting. So that is this percentage that we are talking about. Type 2 is basically on the thin films, like this chalcogenide thin films. Type 3 is the most attractive, and here what you see is that this efficiency you can reach really high, but the cost we can keep it low. Okay? Now we have to go for type 3 now. So the generation 3. So generation 3, when we talk about, we have these 4 major types of solar cells. Let me start from this side. Quantum dot, the solar cells, we worked on it, and the maximum in the world we have gone up to 16%. Okay? Now these organic solar cells, 17%. And let me tell you, when I write these percentages, people have been researching over it, but those percentages have reached here. It is not going beyond that, and that is, I'm talking of over the last 10 or 15 years. So the fields have become saturated. Okay? Now, dye-sensitized, the solar cells, this Switzerland the airport, you have some of the panels which are made by dye-sensitized the solar cells. The most attractive now is this perovskite solar cells, and which has reached up to 26% by now. Okay? Now, if you look the perovskite solar cells, I'll tell you a brief about it. We also work on it. So we start from 3.8% in 2009, and 2020 it reaches 25.7%. Okay? You see the jump in this enter efficiency. It's a huge jump, 25.7%. These are all single junction solar cells. Okay? Only a single junction is there. You have the photoactive layer, one layer on top of it is taking away these electrons, and another layer below it is taking away the holes, because when you shine light, you create this electron and holes, right? So they are all the single junction solar cells. Now this is what a typical perovskite looks like. This is the crystal structure of it. It is given by ABX3, you can see ABX3, and A side you have these organic cations like methyl ammonium, the formamedium, etc., or you can have the largest cation of the periodic table, which is the CS+, the cesium. At the B side, you have lead and tin. Now lead is, of course, that is toxic, but when we are using it for the solar cells, we are not consuming it, so we are still fine with that. Okay? We don't consume this solar cells. If I say that, okay, I'm going to use a lead based for these biomedical applications, then it is of course a problem, but not for the solar cells. And we have this halides. The beauty of this this perovskite is, you see that this is the valence band, this is the conduction band. I think all of us know about the valence band and conduction band, right? You see that there is a band gap. For most semiconductors, what happens is that you have the mid gap the trap levels, which trap these electrons and the holes. Okay, this perovskite is such that if it's lead based, these trap states, they stay at the bottom of the conduction band. So the band gap will remain free most of the time. The band gap remains free means you do not have the defect states. So it becomes defect, tolerant. Plus it has a lot of beautiful optical properties. I'm not going to tell you here. This objective of this lecture is different. All right. Yeah, so this is the perovskite single junction solar cells. These are some of our work, the slide is. So we work on the nanoparticles. For the semiconductor nanoparticles, you call them nanocrystals. And here, if you change the band gap, you see these beautiful colors that come from the green to red. Okay, you have just had to change the halide. So here it is only the BR3. Here you have the BRI2. So from the green to red, you can have a wide range of the colors because the band gap is changing. It absorbs at different, the regions of this electromagnetic spectrum. We have consistently got 20% of this efficiency. Now this is a perovskite solar cell, that how it looks like. You have a glass, this is a conducting glass, compact titanium dioxide, which acts as the electron transport layer. You have this, this is the photoactive layer which absorbs the sunlight. This is the hole transport layer, HTM, means it takes away the holes, and this is the top contact, the gold. Okay. Now getting 20% efficiency, and they are not very, the moisture stable. So if you keep them outside, you see that over 35 days, there is a less than 20% drop in this efficiency. At the lab scale, these are all fine. Okay? We can publish some good papers, you can see here, but when you talk about the real applications, this is nothing. This is nothing. So, so people have to think of something very unique. First thing is that all these efficiencies that you see that I have showed from 2009, 3.8% to 25.7% in 2020, all were made with very small area cells, less than 0.5 centimeter on just each side. So 0.5 by 0.5 centimeter means 0.25 centimeters square is nothing, right? How can you make a huge panel? Whenever you try to make a big panel, this efficiency will drop, and it will degrade in the air. So the main thing is to increase the size of these panels if you are talking about a single junction solar cells. So there are various reports where these panels could be made, and suppose this is, you see it is 55 centimeter square, and they have tested the thermal the stability at 60 degrees C, and with 82% of this efficiency is there. Now there are various such examples where people have made up to 64 centimeters square or 16 centimeters square, and all these reports are there. What is the best way to make them? The best way to make them, these are all the techniques. I am not going to tell you each one of them, but one of them that I will tell you that is very unique and which is very useful is the roll-to-roll processing. So people do that roll-to-roll, this processing, and they can make this type of huge layer of the solar panels, and then they can do it. I have seen my colleagues around the country who have made this, and those work really well. Of course, there is a drop in the efficiency, but being a large area, you can actually digest the drop in the efficiency by 5% or so. If it is 15%, it is still very good, if it's a big panel. Okay, because the silicon solar cells that you have on the rooftop, what are they? 11%? Something they give you. So that should be fine. However, the global photovoltaic market is changing. The global photovoltaic market, what it says, He says that silicon, okay, single junction silicon, the limit of this efficiency is 29.4%. Market needs to increase this efficiency because the demand is high. The supply versus the demand is very high, all right? So the straightforward, the solution is you have the entire electromagnetic, the spectrum. One side is a red, other side is a blue. Red means it is a longer wavelength, right? And blue means it is a shorter this wavelength. So red to blue, you have to change the wavelength. You have to absorb all the light that comes from a very small wavelength to a big wavelength. So you have to change the band gap. So you have to do two things. One is if you have a large band, the band gap, you can absorb the blue part. If you have a small band gap, you can absorb the red part. So basically, one can make a tandem solar cell. So how the thing works is, what has been said, the top cell, so there are two parts of the cell. The top cell will absorb the blue part, okay? Because here the band gap is larger, the top cell. The bottom cell, the band gap is shorter. So the wavelength, it will absorb only those light that have a longer wavelength. So it will absorb the red part. So the bottom cell will have a red part, will absorb the red part. So in that way, you can absorb the entire solar energy that is coming to you, from blue to red. And the base top cell, these are made of the perovskites. Now, if you look at a recent report from KAUST in Saudi Arabia, the paper has not been published yet. This report came this month itself. So they have achieved up to 33.2%, which is a record in itself. And this is a typical, this tandem cell, that the bottom part is made of the silicon and the top part is that of the perovskite. Okay, silicon has a lower band gap, so it can absorb the red part. And here, this, the perovskite can absorb the blue part. And it will pass on the red part to the silicon to absorb. However, a complete perovskite tandem is difficult to make. Why? Because perovskites we have where the blue part absorbing the band gap, okay, you can easily make. But the red part, that is the bottom part, this low band gap, with an average efficiency of 20% is very difficult to make. So this research, this is the gap area that the researchers around the country and in the world are actually trying to solve. So these are the tandem solar cells we are talking about. However, the field of this perovskite has moved on more towards the structure to find new types of phases and so on. You can make in the form of nanoparticles, you can make in the form of the single crystals, and you can find out a lot of papers and articles on it. Okay. Let me move on to the next part on the electric vehicles. I will have to move a bit faster, I guess. Okay, so we do not want to use petrol and the diesel. We have to use either these EVs, as Professor Manna said, and these hydrogen cars. Okay. Now, when we talk about the EVs, okay, the main thing is that it is not only the drive, it is actually the battery. So we have this battery, this cell, we have to put thousands of them to make a module, and we have to make the battery pack. So we have to put many modules to make the battery pack. All right. The most commonly used battery, and in your the mobile phone, the many of you, it is the lithium and battery, and this is the mechanism by which it works. Suppose this is the we charge it, so we have this graphite layer, and we have this cobalt oxide. The lithium goes and sits here into the graphite, and it is fully charged. If you want to discharge it, you see it is going down. These lithium ions will go back to the cobalt oxide. So the main thing is that it has the dendrites which form inside. The energy it is a very good battery. None of the other battery technologies can compete with it. But it has the disadvantages. Let me put it here. The lithium and the cobalt mining, very difficult to achieve. China has occupied most of the mines around the world. So the Congo and other places. So lithium and cobalt to get, because the cobalt oxide is there and the lithium is there, you have to mine the both of them. And the membrane thickness, the typical membrane thickness is around 25 microns. This is a picture of Samsung. I forgot the model number. The Samsung phone which actually caught the fire inside the airplanes. What they try to do, because if the membrane is thick, okay, the charging the process will take a longer time. Samsung wanted to say that we have a phone which will charge in much lesser time. So what they did, they made this membrane thinner than 25 microns. The moment they made the membrane thinner, they used to create this, the dendrites, and the dendrites will pierce through the membrane because the membrane is thin. They move on the other side, create a short circuit, and they used to catch the fire. So Samsung had to take back all the phones from the market and to keep it to itself. And they lost a huge amount of money. Of course, you can understand that. So the membrane is important. If you want to recycle this lithium and the batteries, it is also a very important thing here. So how to recycle the batteries? These are the important areas that this energy sector needs nowadays. And we need alternative resources of the types of batteries. One is the sodium ion, the battery. The method is the same as that of the lithium ion, but I just want to put it that instead of this cobalt oxide, it also is used as an oxide. Okay, it can be a cobalt oxide, iron oxide, nickel oxide, and so on. But the moment the sodium comes, it makes this the sodium, the metal oxide, it changes the phase over cycles. So that's why it is not so good. So, but if you compare any other battery technology, any one technology that is closest to the lithium is actually the sodium ion battery. We have the calcium ion, but the problem here is that calcium ion batteries it is very difficult to move the ions because these are 2+ charge. Then the 1+ charge. So it has this hydrodynamic radius around it, or the diameter around it. It carries the solvent molecules along with them. The more the charge, more amount of the molecules it will carry a load truck to move from the cathode towards the anode side, or from the anode towards the cathode side. So magnesium ions, the calcium ion, they have higher charge, so they are less mobile. So that is only the thing. But the calcium ion, these batteries, they are very safe. It is the 5th most abundant metal that is available. Okay, and the metal batteries, I don't want to go into these mechanisms. Only thing is that it can go through charging and the discharge for lighter applications. One can use it. So these two applications, the reactions which are there, oxygen reduction and oxygen evolution, and this process goes on. We need a catalyst which can reduce the extra potential we need, that is called the overpotential. So then this kind of the metal air batteries can work very well. The good thing about the metal air batteries is since we use free air, so the energy density is very high, but the power density is pretty low. All right? So it is like, if I allow the time, like it is like I just remembered and I want to share that Dhirubhai Ambani, this famous story. He said that he went to the Juhu beach and he said that, okay, I bought some balloons and for some rupees and I sold it for more price because I thought that the balloon has a price, this air is free. So that's how it got in my mind and I sold them at the higher price. That was the start of his industry. So that's what he was saying. So this is very similar kind of a thing. The air is free here. Okay? Photo rechargeable battery, it is just starting. The one person in the University of Cambridge is actually working on it. And basically while you charge, you shine light. You need something that will actually absorb the light. The most common one that is used is V2O5, the vanadium oxide. Now here, during the charging, the zinc ions will move towards the zinc anode, and during the discharge it will come back. Okay, that is how it works here. Okay, I will move from these EVs to the hydrogen fuel. Now here, you need to create this kind of assemblies, and you need to make larger these electrodes. So if you make larger electrodes, again it is a problem. Fuel cells, it will produce this electricity. This has the major the problems are there. Here also you need the catalyst to make good hydrogen, the green hydrogen. And the most commonly this hydrogen is used by the steam methane reforming. Okay? But here you could release this carbon dioxide and the carbon monoxide into the air. So this is not a good this process. The best way is that you will split water into hydrogen and oxygen. But it has to go through a large activation energy. So you need to make good catalyst systems. Myself is a chemist. So you can make a good catalyst to bring down this activation energy. All right? 3 different ways for electrolysis: photoelectrochemical or the photochemical. Let me not go into each of them. I think that this is the best way, okay, this electrocatalysis. Because here at the anode you will release oxygen, at the cathode you will release this hydrogen. And you need the catalyst nanoparticles to sit on top of these electrodes. All right? And so the main motto is that you need more current from less voltage for more hydrogen. I think how much time I have? Anybody can tell me?
Another 5 minutes.
5 minutes? All right, thank you. Yeah. So we need more current from less voltage by applying less voltage for more amount of hydrogen. All right? So we need better catalyst systems. There are different kinds. So these are the catalyst particles. This is the substrate. The substrate also should be electrically conducting. All right? One, let me tell you, this is a basic science, but I think this industry and the basic science has to go hand in hand. So here this is one which is called high entropy alloys. So here you put 5 different metals, at least of 5 to 35 atomic percent of each of them. Okay? Make the alloy. So you have lot of the different ones here. So you can combine this the functions of all these metals into one alloy. All right. The problem is we never understand, and the literature never understands. I have never found out the role of each of these individual these metals. We don't find it. Secondly, there is a lack of the concepts here. Now, in my laboratory, I have actually started a new concept, which is called that we create the defects. In the metallurgy, you deal with the defects a lot. So we create defects at the atomic scale inside the nano structure. So what we do is, when you have 2 different lattices, suppose you have a cubic and this hexagonal lattice side by side, and you want to create an alloy. You use a technique by which you have to alloy them. Very difficult to make an alloy. Why? Because M and N will be separate particles and it will be a mixture. Okay? But can you make them into an alloy form? Can they go inside the lattice of each other? There the chemistry knowledge comes. Okay? But because of the lattice mismatch, the change of this lattice, the volume and other things, you see that there is a gap here when you try to pack both of them. One example I can give you is this silver and nickel. You see the lattice, this mismatch is by 14%. When we try to make an alloy, it creates this decahedra type of these structures, where the nickel stays on the face and silver stays at the apex and on these edges. Okay? So it creates a single particle, but they don't mix up like it is like water and the milk. But they are still there inside the system, but they know where they are supposed to be located. So it happens, and this gives very good results, I can tell you, and that's what we work in our laboratory. Anyway, here is a work which is funded by GAIL India. So what I was telling you about the solar cells, here if you want to increase the electrode size, see here it is 0.5 by 0.5, 1 by 1, 2 by 2, 2.5 by 2.5. This is the extra potential I am trying to say here. This over potential, if you increase the size of this electrode, it goes up. It should not go up actually. But because the mass transfer is very difficult in this case, and it all goes up. And here also, this is for the hydrogen evolution, this is for oxygen evolution. You see that when we increase the electrode area, it is difficult to keep the same activity of the catalyst. Yeah, okay. Another important thing is that we have to look into the neutral water splitting. Okay, water creates hydrogen bonding when it is at the neutral pH. That's why it is difficult to break. We normally see that inside the acidic and the alkaline, this medium, it is good, but it is not always so. So we have got one catalyst which is really good here, and over potential, if it is less, the catalyst is better, right? So here you see that all these catalysts which are available in the literature, and we think that our catalyst is going to be a very good one. Hydrogen storage. If you want to store hydrogen, you have to liquefy it. So you have to go to low temperature. If you want to release hydrogen, you have to go to high temperature. Very difficult to work in this range at room temperature. Okay, that's how this is another gap area. In India, very few labs work in this. So one is to really look into. We can always make hydrogen, but to store it is actually very difficult. Okay, carbon dioxide reduction, many of you know we can reduce it by this electrochemical, photochemical and so on to many of this value added, the fuels like methane, ethanol, everything. We can have these methanol cars or say these ethanol cars also if we can make them, and actually what we get depends on the catalyst what we use. Okay, the last part what I will say is here that I always ask this question, many places I have done. So what is the most important this innovation in the last century, that is the 20th century? Most of these answers come like these aeroplanes, the nuclear energy, computers and so on, which are not bad, which are right, that we had all this. But the most important is not all of this. The most important innovation of 20th century is this, the Haber-Bosch, the process to make ammonia, okay, by reacting hydrogen and this nitrogen. Why? Without ammonia, we won't have these fertilizers, and half the world would have died by now. This population is going up because the medical science, the food we all have here right now. We are at much more comfortable, the situation. So, but these two work under high pressure and high temperature, and because of that, the Haber-Bosch process, it emits 1.2% of the CO2 emission in the whole world every year. Okay, so we need to replace this method now. Both of them got the Nobel Prize, by the way, but we need to replace it now. And one way is electrochemically, if we can reduce this nitrogen to this ammonia. This is another big challenge that we need to address. All right. Okay, so I have told you about these three. And for these energy solutions, we need to work in a team. Okay, one person, a single metallurgist or a single chemist cannot work for it. We need to work in a team, and different fields have to come up, together and solve these issues. And this is our team, and thank you very much.
Thank you, Professor. That was an extremely informative lecture with a blend of popular science, and the lecture have nicely summarizes the state of art and material advancements in peroxide solar cells, lithium-ion batteries, catalysis, and finally hydrogen storage. So we will be having only one quick question from audience. Yeah, I am having. One question.
Who is asking? Can you raise your hand, please? Yeah.
No, I can tell. He is asking in what way we are going to store hydrogen in the material. Solid state hydrogen storage.
Okay, there are two types. One is basically the the chemis option. Other is the physis option. Okay. we have to keep that in mind. Not only we have to store it, but we also need to release it. There are materials which can store it, but they cannot release it. All right, you have to create and break the bonds at the same time as you need it. So that's what this the liquid hydrogen forms at minus 250 degrees I think centigrade, if I am correct. And releasing needs high temperatures, like 300 degrees C or so. So both sides need to be taken care in this case.
And just sorry to interrupt, we have this whole day and professor is with us, and we have a panel discussion also in the second half, and we have enough time to interact. So please make use of that one. We are running short of time, so I will just
Thank
move
you
ahead.
so much. I can answer anything you have afterwards.
Yeah. You're free to interact, and that is the purpose of this event. Thank you. Thank you, Professor. So going ahead with our lecture series, now I request Professor Preeta Pan to present her lecture. Professor Preeta Pan received her MS and PhD degrees from Material Science and Engineering Department at Cornell University, USA. After postdoctoral research at Cornell and Harvard Universities, she joined IIT Bombay as assistant professor in the Department of Metallurgical Engineering and Material Science. She is currently the professor in the same department. Her broad research interest includes microstructural changes that occur during deformation and their effect on the mechanical behavior of materials. Her group carried out series of experiments on bulk and microscale deformation, utilizing optical electron microscopy, also molecular dynamic simulations. She has guided 8 PhD students and several master students at IIT Bombay. She teaches both undergraduate and postgraduate courses on mechanical behavior at bulk and microscale, and as well as the computational methods. With this brief introduction, I request Professor to present her lecture.
Hi, thank you for the introduction, and thanks to all the students who are sitting here patiently. I will stick to the time. So this is going to be a very different talk. Professor Manna sort of started in the past, took you to the future. I think Sayan showed you what the future, where it will lie, and what needs to be done to get there. I am going to take you to the past and stay firmly in the past. And that is because when I was asked to come and give a talk here, the topic was kind of spelled out for me, and the topic was really grand. The topic was some materials and civilization. And you know, I'm not an archaeometallurgist, I'm not a historian. So I said, okay, I will try. And when I started trying, I realized that there is no way I can speak on something which is as broad as materials and civilization. So I started shrinking it and shrinking it and shrinking it. And now I've shrunk it down to one topic, which is basically wood steel. And with that disclaimer that I'm not an archaeometallurgist, I'm basically going to try to tell you a story. Okay, the story that I learned in the last couple of weeks when preparing for this talk, and it's a fascinating story. So hope you'll also find it interesting. And in the end, you know, I'm a teacher. So teachers sort of, no matter what they do, they feel like they should impart some lesson. So in the end, we'll see whether we can draw some lessons from the story. So let's go ahead. So I'm going to start with two characters, Faraday and Stoddart. The name Faraday would be familiar to you. Stoddart may or may not be familiar to you. And this is in London. So from 1819 to 1824, when Faraday was 28 to 33 years of age, he did a whole bunch of experiments related to alloys of steel with about 16 elements. Right? This is something that was not, it's not very well known, right? When we think of Faraday, we think of other things, we don't think of steel. But Faraday, as a not so young researcher, spent a lot of time working on steel. And the story is about why was Faraday working on steel and what came out of his work on steel. And this content is from a paper that Hadfield has written. Again, the metallurgist would be familiar with this name, right? He has lent his name to steel itself, Hadfield Steel. So Hadfield has written a paper on Faraday's work later, and he says that, look, there was a paper co-authored by Mr. Stoddart and Faraday, which was read in before the Royal Society in 1822, and it's called On the Alloys of Steel. And what he says is that, look, although there are these two co-authors, when I look at the work that is presented, it is very clear that all the work has been done by Faraday himself. Okay? So all the work of preparing the alloys was done either by Faraday himself or in the later case under his instruction. So he says the credit all goes to Faraday for the work that was done. It turns out that Stoddart is sort of the inspiration and the funding agency behind the work, right? But what is this work that Faraday was engaged in? So let's look at first the motivation, the funding agency, which was Stoddart. These are his visiting cards. I don't know how many of you can read it from back there, but what it says here is, what J. Stoddart, and this is where his shop is, 401 Strand, London. Surgeons' instruments, razors, and other cutlery made from, and this word I'll show you later, it is almost in Devanagari script, and it reads as Uts, but in bracket he writes Woods. A steel of India preferred by Mr. I think this is J or Mr. S to the best of Europe after years of comparative trial. So this is his visiting card, which is also like a certificate of appreciation to wood steel. That I've looked into all sorts of steels and I've found that this is the best. And what does he do? He says, I am a maker of surgical instruments, cutting tools, and cutlery. This is another visiting card, which probably now gives you a clue. It says, Stoddart Surgeons Instruments Maker to the Army and the Honorable East India Company, London. Okay? So these are his visiting cards. Like I said, he's the funding agency. And now let us look at this wood steel. What is it that Mr. Stoddart is putting on his visiting card? And this is a steel best known for making weapons, right? So swords, etc., etc. And there's actually a nice book if you want, and this book is available. There's a PDF of it available, written by Sharada Srinivasan, who is in fact an archaeometallurgist, and Professor Ranganathan, who until a few years ago was a professor at IISc. So they say that, in the book they say that the fame of steel from India is well captured, and what this person is saying is that the Hindus excelled in the manufacture of iron, and it is impossible to find anything to surpass the edge from Hinduvani or Indian steel. And here is an image of a dagger which shows a little bit of detail of that steel which is being used to make these daggers, and this is this wood steel that we find that Faraday is interested in and Mr. Stoddart is interested in. Yeah, now steel, Professor Manna kind of referred to it in passing, that steel, or for that matter its parent iron, is not something that you can go around and find, right? It's not like gold or silver where one could have found nuggets and figured out what to do with them. This has to be made because it occurs as an oxide, except for there are some places where there is meteoritic steel, and Greenland is one such places where the Inuit Indians have used that meteoritic steel. In Egypt, apparently the pharaoh Tutankhamun was found buried with an iron sword and a gold sword and so on, and when that exhibit traveled to museums around the world, because iron was considered so precious, the iron sword was kept back in Egypt and the gold sword was sent with Tutankhamun, because that was not that important. Even if it gets lost, it's okay, we'll make another one. So this is an image from a meteoritic steel, in fact, which underwent very, very slow cooling. And again, the metallurgists will appreciate this, that you can see this Widmanstatten structure, which otherwise is really fine. You can only see it at the microscopic level, but here you can see it, a really coarse structure, which usually is not available. So let me quickly take you through the Iron Age in India. That it starts in late 2nd millennium BC, and India has already achieved excellence in wrought iron production by the 1st millennium AD. And you would be familiar with this, I think everybody is familiar with this is the iron pillar in Delhi, which people talk a lot about, right? The fact that it hasn't rusted, or it has rusted but it's still standing there. And this is from about 8400. Okay, and what I find fascinating is that people could make a pillar with a height of over 7 meters, a weight of about 6 tons. Remember, there are no cranes, there are no mechanized instruments. So this has been made by hand with hammer forging together lumps of iron. Either it was made horizontally and then stood up, or it has been stood up. There are all sorts of interesting drawings available. So there is one drawing which shows people standing on stairs, and the stairs are going up and up and up as the pillar goes up. And then the corrosion resistance, there are again lots and lots of papers on it. I'm citing only one. This is by the late Professor Balasubramaniam of IIT Kanpur, who basically said that, look, this pillar has a high phosphorus content, higher than what is commonly found, and it could be that has made a protective surface layer, which is what is protecting this pillar. But I will talk a little more about it, not particularly about the pillar, but about corrosion resistance. I think Dr. Singh just walked out. He's the expert on corrosion, so I'll speak a little, and if there are more questions, we'll direct them to him. So, not about the iron pillar, but about a community of people who were called Agaryas. In fact, when Dr. Singh first called me and said, will you give this talk about materials and civilization, I suggested an alternate speaker to him, which is my colleague who's now retired. His name is Professor Ballal, N.B. Ballal. Some of you may know him. And he has actually visited them, spent time with them, worked with the Agaryas. And there is a phenomenal talk that he has given, which was part of a TEDx talk at IIT Bombay, which you should listen to. As talks go, as technical talks go, it's absolutely fascinating. So, why am I talking about Agaryas? Because I'm about to show you some results from a paper published relatively recently, where people said that, look, they were interested in understanding the corrosion resistance that came from iron made by the ancient iron making technique, but you obviously cannot walk up and take a slice out of the iron pillar. So the alternative is, they feel that technologically the Agarya process was similar to the process that must have been used to make the iron pillar. So this person has in fact done a very detailed analysis of iron made by the Agaryas. And this is from the anthropologist Verrier Elwin, who again spent a lot of time and studied the lives of the Agarya people, of other tribal people also. And he makes this statement, says that these are the people absorbed in their craft and their material. They seem to have little life apart from the roar of the bellows and the clang of the hammer upon iron. I don't know, there are how many PhD students here, but this is what an advisor expects from an ideal PhD student also, right? Little life aside from the problem that you're trying to solve, at least for the few years that you're trying to solve the problem. So otherwise you don't become very good at what you're doing. So this is the furnace. This is a schematic of the furnace. I'll also show you a photograph. These are bellows, foot operated bellows, from which you pump air into this furnace and you try to reduce the ore to iron, reduce the oxide basically to iron. Okay, and this is completely manually done process. So this is from Professor Ballal's visit to a furnace at Bishanpur or Bishanpur, I think, near Netarhat. He visited this place, he visited this person who had built this furnace from memory, from whatever he remembered as a young person, his grandfather or somebody doing. He built this furnace, and this professor from IIT Bombay went to go study how the process used to work. And this is just a screenshot from his TEDx talk. And then he was fascinated. He went and visited other furnaces in the neighborhood. So these are other furnaces. So there's a furnace at Balghat, there's a furnace at Wadruf Nagar, there's a furnace at Sela. This furnace is owned by this lady. Okay? And then he was fascinated enough that he conducted a workshop at IIT Bombay where he invited people who used to make and work with these furnaces. So this is the furnace that was made at IIT Bombay. And there's a story associated with it which Professor Ballal used to tell. He said that, okay, so he's organized this workshop on indigenous iron making. The furnace has been made and it has to be fired. And this community of people, so I think Lohasur is the god that they worship, who kind of sits in the furnace and leads to this reduction. But they said that, look, before we can fire the furnace, the gods have to be appeased. And how do the gods have to be appeased? A sacrifice has to be made. Now remember, this is an academic campus. This is a furnace inside an academic campus as part of a scientific workshop. And those of you who have ever organized a conference, if you think your speakers are giving you a tough time, think about this. Now your plenary speaker tells you, I cannot do anything unless we sacrifice a goat. And this professor says, now look, I cannot possibly sacrifice a goat, right? I can't do this here. So negotiations happen and finally they agree to sacrificing a chicken. So a chicken is brought, duly sacrificed, and the gods are appeased and the furnace is fired. What Ballal deduced from this was, remember we were talking about phosphorus. So what he deduced was that, I don't know which part of the chicken actually goes into the flames, but he said that the bones probably become sources for phosphorus and also some amount of calcium. He said that was the science part, the rest was, the rest was appeasing the gods, which we will not go into. But that was his theory. He said this is the source of phosphorus that goes into their iron. So why am I talking about all this? Because these are the samples, which then there is this paper from 2021, right? Not too long ago. This is some Dwivedi et al. This is a group in Australia. So Curtin University in Australia, and they were interested in, so they've taken samples from agarias in this Amadand Korba in Chhattisgarh, and they have done a whole bunch of advanced analysis on this. So they've done XRD, they've done EDS, they've looked at it in SEM and so on to try to figure out. It does get corroded, but this is the corrosion layer. These are SEM images of the corrosion layer. So this is the top view that you see, this is the side view that you see of a section. This is the substrate and this is the top view. And they find that this corrosion layer basically consists of iron oxide, silicon oxide and calcium carbonate. And this layer is adherent enough that it then stops the further corrosion of the material underneath. So it's not that it is corrosion resistant, but the corrosion products are adherent and hence passivating. So they protect everything that is underneath. And the other interesting thing which they looked at, remember these are the pillar that I was talking about. I said it is hammer forged. You take one lump of iron, you then take another lump of iron and you hammer them together. I mean, you can go back and look up images of this iron pillar. It doesn't look like separate lumps sitting on top of each other. It looks like a pillar. But remember, this has been small pieces hammered together to this smooth surface finish. So these folks also looked at the effect of hammering. So I'm sorry you cannot read this scale. This is basically thickness of the surface layer, where red is the highest thickness and there is green and blue is lower thickness. This is an unhammered piece of iron and this is a hammered piece of the same iron. And you can clearly see that the thickness of this surface oxide layer, which then protects everything underneath, that significantly increases post hammering. And they gave some explanation for it, which I don't quite understand, but they basically said that, look, hammering gets rid of internal pores or agglomerates certain internal pores. And it probably also, so there is slag entrapped in this. This is not a molten iron process. There's slag still entrapped. So it gets the slag to the surface, which probably has the elements which are required to make the oxide, which then helps to make this oxide. So that cold working or cold forging
also plays a role in improving the corrosion resistance. Now let's come back to wood steel, okay? I have, I think, 10 minutes? 12 minutes, okay. So we have to get through this in 12 minutes. Remember, Mr. Faraday, we still have to come back to Faraday. I have to close the loop. So this is an image of wood steel. It was called, I think there is a, yeah. So I found this description very, remember I'm a scientist. I sort of tell my students write in short sentences, crisp sentences, to the point. But over the last few weeks I've been getting to appreciate poetry. Poetry which describes science. So there is an Arab poet who is describing the surface of a Damascus sword which looks like this, which is made from this wood steel. And it says it has a water whose wavy streaks are glistening. It's like a pond over which wind is gliding and so on. Okay, this is the first time I've read somebody writing poetry about what is essentially perlite and cementite macrostructure. So it was kind of fun. So where was this wood steel being made? Well, in India, it was being made at several places. It was being made near Hyderabad. It was being made in the south of India. At several places. It was being made in Sri Lanka. And later it was also being made in Central Asia and so on. And from Hyderabad, this steel was being shipped to Damascus, where the swords were being made. It's essentially a high carbon steel which contains about 1.5 to 2% carbon. Its utility in making swords is it has high hardness, right? So once you fashion a cutting edge, after slicing a bunch of heads, it doesn't get blunted. That's what we like about swords, right? So, okay. So where does the word come from? So Sarada Srinivasan talks about the etymology. She said that it probably comes from the word ukku, which European travelers must have heard in the Kannada and Telugu speaking regions of the south of India. And she says that this basically 300 BC up till about 1856 AD is the first age of steel, when this crucible steel making became sort of a perfected process in India. And what were people doing in this crucible steel making? So here is a more detailed image of where all it was being made. And from this, I'm going to take maybe 2 slides to talk about Sarada herself, her findings at this place called Mer Siruvalur. I'm sorry, I'm probably mispronouncing all of these places. But so she did excavations at this site and then tried to recreate what could have been happening. Okay, so various places where it was being made, sorry, before I go to that, and there were subtle differences. So in Hyderabad, what people were doing was they were taking 2 pieces, one was high carbon, higher than what you needed, one was low carbon, and then fusing them together so you get something which is intermediate, which is about 1.5 to 2% carbon. When we teach you composites, we say this is what you do, right? Take 2 dissimilar materials with dissimilar properties, put them together to get something which is intermediate, which is what you want. In the Mysore process, this wrought iron was being charged with carbonaceous matter, which was pretty much organic matter. It was leaves, it was husk of things and so on, which was then burnt in a reducing environment so that the carbon went into the iron. Again, solid state diffusion. Things were not quite getting molten. And in the Salem process, only wrought iron was being charged because I believe the crucible itself was providing carbon. It was proving to be a source of carbon. So here are some of the broken crucibles that have been found, and these crucibles were actually coated on the inside and on the outside with a glassy substance, which they say must have been the slag that was used during this charging. And what else do they find? So imprints of leaves and grass, probably used as the carbonaceous material. Presence of glassy slag is there, and they found, so they did find rusted pieces of metal here and there and so on, but those were rusted. So they couldn't say what did the people actually make, but they found pieces of metal embedded in the glassy slag. And when they analyzed those, they found that they had a pearlitic structure surrounded by intergranular cementite and a carbon content of about 1 to 1.5%, which is what we've been seeing later. So I'm going to skip this, but this is the timeline, starts at about 323, but I want to come here where it says, Yeah, 5 minutes, right. So 1820, Michael Faraday and James Stoddart erroneously attribute the quality of wood steel to silica and alumina. And then people in France, they study. So this wood steel that we've been talking about, being made in Hyderabad and the south of India, has now by 1820 made its way to England. And is being studied in the labs of the Royal Society. So how did it get there? So it says a Scottish surgeon who was in the Bombay Medical Service sent samples of wood steel to the Royal Society, to a person named Joseph Banks, and who ordered that they be investigated. Okay, this was a surgeon. Remember, he's interested in cutting tools. People slicing heads are not the only people interested in cutting tools. And Joseph Banks passed it on to a physician in London and the rest to Mr. Stoddart, who immediately appreciated its value. He said, it's a really good quality cutting steel, and can we figure out how to make it? And thus comes into picture Mr. Faraday. So Faraday was concerned with making a steel that could make better knives, surgical and cutting instruments. This is Faraday's writing, where now he's writing this word UTS, sort of, which looks like UTS. He's probably copying it from somewhere, because Faraday, remember, lives in London. He doesn't know Devanagari. He's never been taught Devanagari script, but this is his sketch. So that was his goal. He was given a piece of excellent steel whose origin was not known to him, and he was told, well, reverse engineer it. Figure out how this works. So he worked hard. So this was his object, whether any other substances were present in woods, any other substances than iron. And so he did a series of experiments on the alloys of steels, though the goal was imitating the woods, but I would like to draw your attention to a series of experiments on the alloys of steel. This is among the first times that this term alloys of steel comes up. Okay? And you've already heard a lot about how versatile steel is and so on and so forth. So he had available to him, he had a small furnace. Here are the bellows, here is where the carbon goes, here is where the iron goes, iron or whatever else. And he was very systematic and very, very hardworking. Look at this. He experiments with 13 of these elements, going all the way from copper, gold, noble metals to titanium. Non-metallic elements, carbon, silicon and sulfur, there are 16 here, and other ferrous substances, woods or Indian steel, alumine alloy, which is basically aluminum oxide and something, and meteoric iron. So he spends his time adding all these things systematically to iron and seeing what he gets. And what he gets is, to a large extent, was preserved in this box, which has the label Faraday, from which these specimens came, which were then later analyzed in great detail by Robert Hadfield, who then said that, look, Faraday did something phenomenal. But, so this is all that came out. There are ingots, there are blooms, there are strips, there are also objects. He also made spheres and so on. Okay? So when Hadfield looks at it, now he classifies them into 3 or 4 groups. The first group is where the carbon percentage is increasing fairly systematically. This is also, it's a nice long paper. And he's done all sorts of hardness studies, magnetic permeability, this, that. The second group is where other elements are being added. Everything from chromium to platinum and rhodium is being added and tested. And the third group, which is now a ternary, platinum and silver in iron, silver and gold in iron, nickel and gold in iron. So what came out of it? According to Faraday, nothing. All this hard work, and what does he say? He writes to his friend. This is just a few years before Faraday died. He says, pray pity us that after 2 years, and it was in fact not 2 years, it was about 5 years of work, we have got no further. But I'm sure if you knew the labor of the experiments, you would applaud us for our perseverance at least. So he works really hard for 5 years, and he's completely devastated because he's not really reproduced woods. But he's been hard at work. So, this is from his obituary, sadly enough. It says the results of the paper on steel by Stoddart and Faraday were of no practical value. And this, one of his first and more laborious investigations, is strikingly distinguished from all his work by ending in nothing. The reason I'm saying this to you is such is the nature of research. You start with an idea and you put your heart and soul and blood and tears into it, and you don't know where it will go. That's why it is research. And sometimes it may seem like it ends in nothing, right? But because it may end in nothing 5 years down the line, you cannot stop here and say, but you know what, I'm just going to cut corners here and not add the 6th element and not test the 7th element. Because what Hadfield concludes later, he said, does it really end in nothing? He says, look, this is everything that Faraday accomplished. This is my last slide, don't worry. This is the first systematic study of the alloys of steel. He determined at that time, with the limited instrumentation available to him, the solubility limit of silver in steel to be about 0.2%, which is actually correct. He determined that there's no limit on the solubility of platinum and rhodium. He found that addition of nickel reduces the tendency to corrode. He determined that high carbon steels rust more readily than low carbon steels. He found that rhodium makes the steel resistant to softening by tempering, which is what was used in high speed steels later. Things that get hot, but they still don't lose their strength. So it actually did not end in nothing. It is just that appreciation of the value of the work that he had done came much later. In his case, after he had died. Okay, so with that, I'm going to stop my story. Thanks for listening. And you know, I found it fun to read these things. I've been teaching for many years, and it was fun to read this story. So, and if you have questions, I can answer them, or you can ask me questions over lunch or something.
Thanks, Professor, for an interesting lecture filled with historical and scientific insights about Indian ferrous metallurgy. So going forward, I request Dr. Sanjay Kumar to present his lecture. Dr. Sanjay Kumar is currently Chief Scientist and Head Metal Extraction and Recycling Division at CSIR-NML. He is also a Professor in Engineering Science at Academy of Scientific and Innovative Research. Dr. Kumar is having 28 years of research experience in the area of recycling and solid waste management, strategic metals. He has edited one book, co-authored 4 book chapters, published 146 papers with more than 6,000 citations. He also has 25 patents to his credit. He has guided 3 international postdoctoral fellows, 5 PhD fellows, and 9 MTech students. He is on the editorial board of 2 reputed scientific journals. He is also an expert advisory member of various policy making and funding committees like Russian Science Foundation, Nidhi Aayog, Department of Science and Technology, Ministry of Environment, Forest and Climate Change. Dr. Kumar has commercialized 3 technologies as a main inventor. In his career, he executed 5 national, 4 international, 6 government-funded projects, as well as 45 industry-sponsored projects. So with this brief introduction, I request Dr. Sanjay Kumar to present his lecture. Thanks.
Thank you, Prem. Good afternoon, everybody. I have been given a Herculean task to cover about 2 organizations, our parent Council of Scientific and Industrial Research, having more than 80 years of legacy, and CSIR National Metallurgical Laboratory in 30 minutes time, which is almost impossible thing. So I will touch upon, I will not go much in detail, but I will only touch upon the important things. So just you can see all the logos in the top. We are president of G20, and CSIR is part of all the scientific event of G20. So if you take the history of CSIR, I will say World War II has played a very important role, both for the history of CSIR as well as for the history of National Metallurgical Laboratory. What happens, the discussion for CSIR started in 1937 by the British people that India is such a rich resource country, we should have the technology in India, so we should not take all the raw material to England and then make product and then return it back. And so the discussion started, and then the World War broke out in 39. And immediately they have taken the decision to set up CSIR, and two Indian scientists, Dr. Mudaliar and Dr. Santi Swarup Bhatnagar, they were instrumental. They have made the constitution of CSIR they have written, and in 1942 CSIR was established. And today CSIR is the largest research and development body in India, and among one of the top publicly funded company in the world after CNRS and Fraunhofer, Germany. So in the 1943, just after the establishment of CSIR, the governing body of CSIR decided to set up 5 laboratories, and NML was one of that, which was planned in 1943. So this is the structure of CSIR. The Prime Minister of the country is the President of CSIR, currently Honorable Narendra Modi ji, our President. The Minister of Science and Technology is the Vice President of CSIR Society. Dr. Jitendra Singh is our Vice President. And Dr. N. Kalai Selvi is the Director General of CSIR and Secretary of DSIR. She is the first female Director General of CSIR. And if you see the structure of Ministry of Science and Technology, they have 3 bodies, DST, DSIR and DBT. And under DSIR, CSIR is the autonomous body with 37 institutes, 39 outreach centers and 5 units. And we have, as on 31st March 23, we have 3,439 scientists in CSIR. The support staff are 4,193 and administrative staffs are 2,540. And we have more than 5,500 PhD students in the CSIR. So the vision of CSIR is very much aligned with the vision of the country, where we are talking about the enhancing quality of life of the citizen of India through innovative science and technology. And we are also talking about taking the global leadership in science and technology. So we have 37 laboratories, and the presence of laboratories are in the 25 states of the country. And the whole CSIR laboratories and the research work has been divided into 9 theme areas. The theme areas starts from aerospace, electronic, instrumentation. You can just read out. And we are falling under the theme 7, that is mining, minerals, metals and material, which is also called as 4M theme. Under this theme area, there are many sub-verticals as well. And today, we have 25 subject domains, 3,200 active patents, one of the highest in the world, then 5,647 SCI publication, and more than 900 technologies which are active. And our theme areas are aligned with the national mission as well as SDG goals. So you can see we fit into like NML. It is contributing towards many of the national mission program like Swachh Bharat India and Made in India, like that. So all the laboratories, they are contributing towards 1 or 2 or 3 of the mission programs, as well as we are addressing more than 30 SDG goals out of the 13 SDG goals out of the 17 goals. And these are some of the indicative developments, because speaking about development taken over in 80 years across the country in under 37 laboratories is very, very difficult. So these are some of the indicative technologies where CSIR has worked, developed the technologies, like mining technology. Lot of work has been done on farm mechanization, energy storage devices like that. And some of the recent initiative taken are green hydrogen. We have started a national mission on green hydrogen, where we are trying to look after the whole cycle of hydrogen, start from the material for hydrogen storage and everything. NML is also contributing. Then we are working on carbon capture, utilization and sequestration. This mission mode program has launched recently. Then water for all, we are working, sickle cell anemia and aroma and floriculture mission. I will just touch upon few of the recent technology which has changed the life in the country. One of it is aroma mission. It's a very popular mission which was launched by the Prime Minister with an objective to bring the 60,000 hectares land under the cultivation of aromatic plant and increase the production of additional 700 tons of aromatic oil, which is used in perfume or cosmetics or pharmaceutical industry. This has given a business of 200 crores and around 1.5 lakh people have got employment. Then as a part of aroma mission at the time of COVID or just before COVID, Prime Minister has launched a purple revolution, means cultivation of lavender, which is a very important flower for the perfumery. So this has started in Jammu and Kashmir and Uttarakhand and the cold places and also in the northeast area and is very, very successful. Now if you go to Jammu and Kashmir, many part you can see lot of land is purely purple with the lavender flowers. So this has changed life in that area like Jammu, Kashmir, Uttarakhand and northeast. Another very important contribution of CSIR is in the light combat aircraft Tejas, which has been adopted by Indian Air Force, where many of the technologies of this vehicle was developed by our sister laboratory, National Aeronautical Limited Company. So, and the very recent is the use of steel slag in the road making, developed by one of our sister labs, Central Road Research Institute. It was adopted by Border Road Organization, and now Tata Steel is also part of this mission, where they are supplying the steel slag after processing it by the process developed by CSIR, and this has been used at many places. And very recently Niti Aayog visited at one of the place, and they said that this type of road can also be used for runway making. Now coming back to our this is a very important thing, especially for a student. As a part of CSIR, Academy of Scientific and Innovative Research has been started by the Act of Parliament in 2012. It gives the PhD integrated dual degree program, MTech plus PhD, MSc PhD, MSc Masters in Public Health, MTech and PG diploma. And this ACSIR is ranked second in the Simago institution ranking, 11th by the Nature Index and 18th by the NIRF ranking. And last year we have produced 577 PhDs, which is very, very good number for India. No other institute produces this type of PhD in a year. And we have 6,100 enrolled PhD students. So any of the student who is looking for MSc or PhD in any of the area aligned with CSIR mission, they can consider this. And CSIR is also supporting the venture capitalist or incubation centers, and we have lot of incubation center, like one at our National Chemical Laboratory, which has supported 380 incubators. Like you can see the list in the right side. Since the time is short, I am not reading out all, but we have many incubation center in the different part of country. And NML is also having the incubation center. So anybody is having an idea and want to incubate their idea in an institute of CSIR, they can just come to CSIR. So coming back to this institute, CSIR National Metallurgical Laboratory, it was opened in 1950 by Pandit Jawaharlal Nehru, who in his opening statement said a very interesting subject. You can just read out the combination of this laboratory with the steel works, which is Tata Steel, of this city, of the marriage of science with industry. You can see the marriage of science with industry is the catchword here, because here we are doing science which is getting implemented at the industry. And one of the reasons for putting up the metallurgical laboratory in Jamshedpur was this area is very rich in mineral resources like iron ore or copper ore or uranium ore. So whatever metallurgical industry will come in this region, they need a support, they need a scientific and technological support. So Tata has provided the land and many other support so that the CSIR National Metallurgical Laboratory could be established in Jamshedpur. So we have done many things which were first in the country, like the first oxygen steel making in India was done at CSIR National Metallurgical Laboratory in the top and side blown converters. And after 3 or 4 years, then Rourkela steel plant has come up using the same technology. So this was the first in the country. During the World War, the import of nickel has stopped in India. We were not getting nickel. So then we were asked to develop the steel which is nickel free, because there is no nickel available in the country. So we have researched in this area and developed the nickel free stainless steel, and you can see like the size of casting we have, and this technology has been transferred. Another was to replace the galvanizing, we have developed the process of aluminizing, and this technology was adopted by many like post and telegraphs for their wires, or Indian railways or automobile industry. This was again a very interesting development which has taken place here, low shaft furnace for the production of pig iron. So what happened when we developed this technology? This was very, very new technology, much before its time. Later on, after 20 years, this technology became very popular in the country. And what we have done is, this plant was transferred to a party in Chhattisgarh who is still running it. The plant we have set up in 60s is still running in the near Raipur area, Chhattisgarh district. And ferroalloy was one of the very important activities during the 60s, and we have put up a 500 kVA submerged arc furnace. We have worked on various type of ferroalloys like ferrochrome or ferromanganese, and this furnace is still working, and we are piloting many of our processes. Our mineral processing, which was started as one of the first activity with National Metallurgical Laboratory, and it was further upgraded in 98 or so, and we have done around 1,100 investigation, and many of our process flow sheet developed here has been adopted by industries in India and abroad, and some of the Indian industries are like Tata Steel is one, Usha Martin is one in the nearby, or ACC in the Jhinkpani. They have adopted the process flow sheet developed here. We were also the first or the only one who produced magnesium metal in the country, and the technology was transferred to a company called Southern Magnesium, who has taken the plant as well as technology, and he ran it till 2000. After 2000, what happened that Chinese have started dumping the very low cost magnesium in the country, so they have to close down their plant. But magnesium is a critical metal for the country, and we need magnesium, and we are totally depending on Chinese import. So this was another very interesting development. Sponge iron by rotary kiln, the technology was given to Andhra Cement, and they have run this technology at 30,000 tons per day capacity plant. Okay. So as they have said only 10 minutes, so I will just browse through, because these are the old things. First time temperature transformation diagram, then the creep building has come up, which was the Asia's largest creep facility, now second largest, as Japanese has put a bigger facility. We started the component integrity evaluation program, which converted into a structural integrity assessment activities. We have done lot of failure analysis. It was one of the activities which started during 60s and then further consolidated, and we have done lot of analysis for crashing of planes like Sukhoi we have done, or many type of failure in the hydel systems. We have done the blast furnace modeling, and a real-time process simulator has been developed and was put at Bokaro steel plant, which is still working. We have done lot of work for artisans also, the rural technology. After 2000, lot of new area opened in the National Metallurgical Lab. We got a director who was visionary. So he has started many area which were futuristic, Dr. P. Ramchandra Rao. So we have started working on column flotation, and this is one of the success story of National Metallurgical Laboratory. We have commercialized 8 column flotation. We have 1 pilot scale column flotation and 5 laboratory scale column flotation given to the different parties, and the largest column flotation given was 1000 tons per day capacity. It is for the barite ores. Dry beneficiation started as one of the important activity because water availability is very scarce in many of the places, and 2 of the major activity are still undergoing. One is dry beneficiation of high ash Indian coal, and another is dry beneficiation of low grade iron ore, and Coal India is one of the collaborator, especially CMPDI. So this is another activity where we are making coking coal from non-coking coal, and in another interesting development, we are using the oil agglomeration to reduce the ash content of the Indian coal, which is normally very high in ash percentage, more than 35%. Strategic metal is very important for the country because these are the metals which are not available in the country, but you require for your defense, for your military, for your space planning, for your renewable energy, for your electric vehicles, everywhere you need. So CSIR has started a sub-vertical on a strategic metal where National Metallurgical Laboratory is the nodal coordinator, and we are focusing on these metals like nickel, manganese, titanium, tungsten, and all those sort of we are focusing. Some of the technologies we developed, the first technology for production of sodium metal in the country was developed by us, and a pilot plant was set up at Kurnool, where 12,000 ampere cell with a capacity of 2 tons per day is about to come. We have modified our old magnesium process, and we have developed the modified pigeon process, and you can see the magnesium crown in the right side. Magnesium is a very important metal as well as it is flammable. If you keep it open, it will start burning. So even production is very difficult, there is chance of explosion, but now we have a technology where we can produce magnesium metal. We are doing lot of work on the extraction of rare earth metals. We are helping Indian Navy in the Indianization of many of their components and parts. We are part of the national mission on advanced supercritical power plants, where our specific role is mentioned in the right side, where we are studying the creep behavior of many of the specialty alloys. We are working on a strong and tough steel for wear application as well as armor steel. We are working on different type of coatings. Coating has been developed. One very interesting development is we have developed a coating for the ammunition of the, you can see the ammunition. This work was done for the ordnance factory so that the life of ammunition can be increased. We have hot dip process simulator, so lot of advanced coating can be developed. You can see some of the examples here. We are working on functional material for energy and health like magazine and this type of material. This is another area where we are very strong. We have developed devices and sensor which has been implemented in actual practice, and I would like to mention the fiber Bragg grating sensor which has been used in the billet caster for the first time in the world. This is another area where we are very strong, probably best in the country, and lot of activities are going on. We have started a program on fly ash utilization, where lot of process has been developed, few commercialized in the industry. Geopolymer, we are the first to start in the country, and we put up a geopolymer pilot plant, and a road has been made using our technology in the Tata Power. Also, The technology was given to Hindalco for making paving blocks from their red mud. We are valorizing iron ore slimes, which is a waste material for from the beneficiation of iron ore, and we have developed coolant for LD converter. You can see we produced around 100 tons of slime, which has been tested at Tata Steel and further adopted by them. This is a national mission mode project on holistic utilization of red mud, where the main objective is to extract scandium. Scandium is a rare metal which is not in the country, and red mud is the only known source for scandium. So, we are trying to recover scandium as well as use the red mud holistically. This project is monitored by Niti Aayog. We have an umbrella program on e-waste management, where we are taking care of devices, batteries, magnets and opto devices. And this program has converted and given us a urban ore recycling center, which is the first urban ore recycling center in the country. And here we are processing different type of e-waste in a closed loop cycle. You can see the type of metal and salt which has been produced from this urban ore. We also have very strong activities on the recycling of lithium batteries. We are holistically recycling the lithium batteries, means taking out cobalt, manganese, nickel and lithium, and also giving it back to ISER. They are making new battery from using this recycled material. These are the technology transferred in the area of battery and e-waste very recently. We also produce a certified reference material. We have 38 varieties of CRM which we are marketing. We do lot of research for societal benefits, to name, like we have developed energy efficient furnace for the brass artisans. We have made the DPR for silver artisans. We are part of integrated skill development program of CSIR. We also run Jigyasa program here, where we encourage a student to learn science with fun and enthusiasm by innovative learning tools, and we have a women technology park for empowering women in various areas. And these are some of the future directions we are planning to work. Hydrogen is one area for steel making, carbon capture, additive manufacturing, computational materials engineering, technology for rare earth metal extraction, waste valorization and recycling, addressing the sustainable development goals. And with this, I would like to thank you. I know I am standing between you and the lunch, so you will be eager for lunch. Thank you very much. Okay. Good.
Thank you, sir, for such an informative lecture. We are sure that this lecture will make the students aware more about CSIR and CSIR-NML's past achievements, advancements and their capabilities. So with this, we came to an end of this lecture session. So now we will be break for the lunch, and just a small reminder, sharply at 2:30 we should all be assembled in the same auditorium, and we will be having this panel discussion. Since this is the last day of this OWOL program, we have a lot of programs that should be maintained with a strict timeline. So I request students to break for the lunch. Our volunteers will help you to reach the NML canteen. Also faculties will be, faculties also can be joined, but they will be having a separate lunch counter. Our volunteers are in the auditorium foyer. So please, students and faculties, please break for lunch. And strictly assemble by 2:30 p.m. and we will be starting on time. ये बाहर है, आइए सब।
अच्छा वहाँ देगा क्या? एक दो तीन चार,
हाँ
दो फूल। चंदन आओ। हाँ ट्रेन 4 है। चलो पवन कितना काटेगा? वो तो ला रहा है चाट को और क्या चलो कूपन दे।
डाल दें क्या? ठीक है, आ जा आ जा।
इधर है क्या? ये डायरेक्ट इंट्रोड्यूस करके बैठा देंगे आप दे देंगे।
नहीं बैठा के बोल दो डायरेक्टर को, पैनल को इंट्रोड्यूस करना तो डायरेक्टर को बोल दो पैनल को इंट्रोड्यूस करने के लिए। डायरेक्टर जैसे पैनल को इंट्रोड्यूस करेगा देन यू टेल दैट I think that step is unnecessary, but since you have told and given him a script also.
मैंने क्या मैंने उनको पहले ही दे दिया था बोला पता नहीं उन्होंने ठीक है बोलना है
हाँ नेम प्लेट चेंज करना है, निकालो नेम प्लेट चेंज करना है, पानी चेंज करो। समझा ना?
इसको एक कर देंगे DNML to welcome the guest and his opening remarks।
यस
तो एक काम करते हैं, पैनलिस्ट को बैठा देते हैं, डायरेक्टर को बैठने की जरूरत नहीं है।
डायरेक्टर इज आल्सो पैनलिस्ट है।
पैनलिस्ट नहीं है,
क्या
अभी नहीं रहेगा बोला ना, वो लिखा है तो छोड़ दीजिए।
हाँ
लिखा है तो छोड़ दीजिए सिर्फ उसको। रघु सिंह जी ये बोलिए।
डायरेक्टर इज नॉट द पैनलिस्ट।
डायरेक्टर इज नॉट द पैनलिस्ट।
नहीं है ना
डायरेक्टर इज द पैनलिस्ट, ये किसी वस्तु तो है।
वो क्या है कि he said that he will not be able to stay. I said we can't change any mood now.
हाँ
You stay opening remarks do
हाँ
and then talk whatever.
तो आपको करना पड़ेगा।
2-3 minutes.
वो अगर पैनलिस्ट है तो आपको करना पड़ेगा।
नहीं
Then
you
I-
invite the panelists,
आम्ही
let
panel
them
को
say
invite
it,
कर-
and then you say director to give opening remarks बोल दो।
हाँ।
वो बोलने के
And-
बाद let him sit or let him walk away, whatever he wants to
Right.
do,
Okay.
let him।
ठीक है
ओके ओके
दिया तो है पर्चा दिया है और रखे हैं कि नहीं रखे कहाँ बोल रही
नहीं even otherwise also I think that step we could have avoided।
नहीं इंट्रोड्यूस नहीं करना है, जस्ट वो सब नहीं करना। हाँ ठीक है। हाँ छोटे शॉर्ट करके दे देना।
शिवा सर को to stand and speak, so it will be better for me.
ना
Hello, those who are waiting outside, please take your seat in the auditorium. Good afternoon to you all. I hope that your pre-lunch session deliberation was highly beneficial for all of us present here, particularly to the participating students. You should agree with me that it is really important to regularly hear from the experts to enhance our knowledge. I am sure that all of you are now excited to hear from our esteemed panelists during panel discussion on the topic, role of CSIR-NML in supporting the scientific pursuit for the development of society. As scientists, we know that the collaboration and the exchange of ideas through interaction are critical to advancing our knowledge and understanding of the world around us. And that is exactly what we hope to achieve with this panel discussion. Without taking any further time, I will take this opportunity to introduce our distinguished panel members who will be speaking about the today's topic on panel discussion. Today, we have Professor Indranil Manna, Vice Chancellor of BIT Misra, and our chief guest of today's function, Dr. Pita Pant, Professor IIT Bombay, Dr. Sayan Bhattacharya, Professor CSIR, Kolkata, and Professor Rajesh Kumar Tiwari, Principal, RVS College of Engineering and Technology, Jamshedpur, and Dr. Abonis Kumar Srivastav, Director CSIR-NML, as our esteemed panelist. I will request our dignitaries to grace the dais, please. Thank you, madam. Thank you, madam and sirs, for providing your valuable time. We are eagerly looking forward to hear from you all. Now, may I request Dr. Abonis Srivastav, our director, to welcome the guest and his opening remarks, please.
So, good afternoon and welcome to this very important program of the day. And before the validity session, last program of this 1 week, 1 lab, that is panel discussion on role of CSIR-NML in supporting the scientific pursuits for the development of society. So that is what we wanted towards the end, that how to reach the science and technology what we are doing in the lab to the society. And this was a comment from our today's chief guest and RC chair, Professor Manna also. So we have a list of panelists here. I think it's better to listen them and then evolve something, some new methodology or something, the way how to proceed further. Professor Manna, we all know, and Professor Pita Pant, Professor Sayan Bhattacharya, Professor Rajesh Kumar Tiwari. So we have very distinguished panelists here. We will hear them in brief, and then we will come out with the kind of some conclusion. And I also hear the name Dr. Shiva Prasad as a moderator for this program. So we'll hear from the panelists and then maybe some quick question answers from the audience, and then we will conclude this session before the validity session. So once again, welcome to this very important event in various ways, and let us participate in the program. Thank you very much.
Thank you, sir, for the opening remarks. Now, may I request Dr. S. Sivaprasad to conduct the session, please?
Very good afternoon to one and all, and my warm welcome to the panelists. The basic objective of this panel discussion is to capture the finer points and to identify the takeaway messages so that we can work on the future improvements in advancement of science and technology to the society. The topic given for the discussion is role of CSIR-NML in supporting the scientific pursuits for the development of society. CSIR in general and CSIR-NML in particular, it has certain mechanisms and certain agendas in covering the scientific pursuits in the region. We conduct a lot of program. We have well-identified program called Jigyasa, right from the school children to the college children. We arrange periodic targeted lectures for both the school children as well as the college students. And we also have the mechanism to support the research scholars periodically. And we also have ACSIR as an academic institute, which also helps in enhancing the human resource development. Keeping aside all these facts, the purpose for which we are sitting down here today, is there any missing points, or is there any scope for improvement so that the outreach to the society can be better? So I have a few targeted questions to the panelists. And before that, I would like to know their individual view on the general aspect of how CSIR-NML can improve upon in addressing to the scientific issues of the society. I would like to start with Professor Manna. A generic view on how CSIR-NML, since you were a part of a CSIR system, you are an educationalist. So in what way the CSIR-NML can improve upon in reaching out to the academic institutes or to the school children to improve upon the education quality and to develop the human resource?
Well, thank you, Dr. Shiva Prasad, and good afternoon to all of you. We are used to a term called corporate social responsibility. Now in the scientific world, another equivalent term is very often used called scientific social responsibility. So the scientific organizations today also are required to reach out to the community and see, majority of the laboratories in the country are under the government funding. I'm talking about the R&D organizations. So obviously, the money flows from government, which means money flows from the common public, the taxpayers' money. So obviously, each laboratory also is obliged to give something back. The question that Dr. Shiva Prasad is posing, how can CSIR-NML do that? Which way? So I would propose a few possibilities, which is not entirely NML specific, but in general, NML can certainly do such things for the neighborhood. Those of you who are in engineering, and or for that matter, not necessarily engineering, I would say, in the scientific disciplines, you hear about various materials, various hardwares, and their properties. That these properties could either be structural properties, meaning which are mechanical properties like strength or deformation, hardness or toughness, or even slightly at an advanced stage, fatigue and deformation under constant stress at elevated temperature called creep and so on. So you get to know about these properties. These are structural properties. Similarly, there are very many functional properties, various types like conductivity, electrical, thermal, magnetic properties, reflectivity, surface topography, surface energy, various properties. To get to know about these details in the textbook is one thing, but to be able to measure and get a feel of it individually is completely different experience altogether. So if you are given, for example, if somebody poses you a question that which will have better elastic modulus, a rubber band or a steel rope? In most of the cases, intuition will tell you that probably rubber band because it stretches a lot longer. But the modulus value of rubber is much too lower compared to the steel rope or steel wire. So just give you an example. I mean, how do you measure the conductivity of copper vis-a-vis steel wire? Why should copper have higher electrical conductivity? So if you do such experiments or see it for yourself, it's a lot better. We hear about a solid material composed of certain constituent phases. How do you see those phases? How do they manifest themselves? How do you prove a crystal structure? How do you estimate certain volume fraction? How do you look at their morphology? Many of these things are difficult to explain in an engineering institution because adequate instruments may not be available or there are too many and so on. So many of you actually can get involved. If NML allows, you can come in a group, see for yourself, see the demonstration, even perform some of the experiments. Many of you can register yourself for internship for 1 or 2 months or even a shorter project. Some of you may have some new ideas of certain measurements or certain device creation. You have a design in mind, you can try it out here. Collaborate with a scientist. Attend some of the lectures which could be very useful to you. This is what in brief, to begin with, I thought this is how you can derive the benefit. But Shiv Prasad, it would be a good idea to ask any of the young fellows here.
I'll go back to them.
What do they expect? What do they, feel important? Yeah.
So anyone can come up. What is your expectation from the student? आप हिंदी में भी बोल सकते हैं.
Maybe you allow first the panelists to respond for 1 or 2 minutes each. Sorry, I took much longer.
It's okay.
Maybe Shayan or Pritha, one of them can respond and then.
Yeah.
Meanwhile, this is a task for you. Each one of you have to raise one small query or suggestion as to how NML could help you pursue your education or future career.
Professor Shah, and I would like to add one more point. You insisted upon, basically what you try to do is, have a hands-on experience in experimental training. We also have a mechanism of creating virtual labs. Almost some of the metallurgical processes, the crystal structures, the basic mechanical testing, we have created some virtual labs. That could be one tool which can have a larger outreach when we cannot accommodate the student. But I want to expect more ideas so that we can incorporate those innovative messages or innovative ideas if there are any. Professor Sham, your views.
Thank you very much. Professor Manna have said in the morning that science is why and engineering is how, right? So these are the two major questions that we have to ask. So I have 3 points to make here. The first point to make is that we have to understand both the sides. So in this case, whenever we are looking for this industrial oriented research, we cannot do without this strong understanding of the basic research. So the first point that I want to make because of this is that the world is moving really fast in terms of scientific research. So, and majority of this experimental work depends on this high-end, these instrumentations. Like when we deal with this metallurgy or this material science, we have to get the access to these atomic scale, like the TEM, this transmission electron microscopy, or a very high-end instrumentation, the kind of these operando techniques, for example, in situ measurements, etc. So I think that a better work can be done if we really understand the problems by looking into this atomic scale of these material systems. Point number 2 that I want to make here is that choosing the right problems or the right the areas of research is very much important. And for example, the defects in this metallurgy field, of course, plays an important role, and a lot depends on it. So like that, like in the this morning, we are talking about these electrocatalytic systems, or the solar cells, or the batteries. So what are the gap areas that we need to understand? And we have to basically find out the solutions to those gap areas. So we have to understand what are the gap areas, then only we can do a good work. And the third is third point I want to make is that scientists, of course, need a vibrant young blood to really work for. So this internship and also the PhD program, if it's there, is that will create a very the vibrant atmosphere in any institute, so that, and many new ideas also can come. So we don't actually enforce our ideas always, we don't do that on the young the generation, because they have a very open mind. So if we have a vibrant young crowd in the form of the PhDs and the interns and etc., the masters, if they can come every now and then that will really like boost the entire system. These 3 points I like to make. Thank you very much.
Thank you. Thanks a lot. Your views, Dr. Tiwari?
Yeah. Good afternoon, everybody. As I am from computer science, I don't have much idea about these material science and all. But 2 or 3 things I want to add. If we consider the premier institutions in India, the students, say percentage is around 5 to 10%. Sir, it is my request, or it is my opinion, that why not we are going to other institutions and rather going for the research, PhD and all, we can take a small problem, we can just divide into small parts, and even we can hand over to the other institutions, even the private institutions, because today the world is entirely open. Even in normal institutions, in tier 2 or tier 3 institutions, we may get a very good students, and they can solve the problems. Thing is, we cannot expect much from the undergraduate students or postgraduate students. So taking a big problem, divided into small part, and just hand over the small part to the different institutions, they will take care of that, they will carry out, and after the results, again they can come and sum up. This may be one of the idea. Another one thing from my side, as a computer science, sir, this virtual lab concept is really very good. Even in our college, we are adopting it. And there are so many other institutions, they don't have idea about it. So for CSIR-NML, this NML, this is my suggestion that they don't have idea. Why not we are making our virtual lab in NML itself? It will be good for the nearby colleges and all.
Okay. So basically, you want to suggest that there must be a virtual lab corner in the lab, and as well as you are suggesting for a collaborative research among the various the institutes. Okay, I take that point. Madam, your views.
I think I like the idea that let us ask the students what they want. So
Yeah,
we've been talking
the
the whole morning. I think we should hear from you what is it that you would want. I have only one suggestion. which is that I think irrespective of whether it's computer science or material science or something else, what the students need to learn is problem solving. Problem solving is an attitude, and problem solving requires, this division between science and technology has to go if you want to solve a problem. And that can be done either we let the students propose a problem, propose a solution, and CSIR kind of facilitates, or NML facilitates a trial of the solution that they are proposing. Give them the means within whatever certain bounds, right? And that, I think, will then encourage them to take up, either it is a technical job or it is research, whatever they choose to do. But this attitude of problem solving will help in whatever career path they take. So some experience of that would be wonderful.
So basically you are saying, suggesting for a crowdsourcing of the problem solving capabilities, go for an open basket of the problems.
Let them propose the problem, let them propose the solution.
Sir, your views?
No, it's better first we should hear the students. स्टूडेंट्स आप लोग इंग्लिश में बोल सकते हो, हिंदी में बोल सकते हो, और आप जमशेदपुर में हो, बांग्ला में भी बोल सकते हो, हम लोग सब समझेंगे, क्योंकि साइंस हैज़ गॉट नो लैंग्वेज, साइंस इज साइंस, इंजीनियरिंग इज इंजीनियरिंग. तो आप अपनी प्रॉब्लम बताइए, आपकी क्या सोच है आप वो बताइए, एंड देन वी विल रिस्पॉन्ड.
Yeah, please. Anyone? Koi? Yeah, please introduce yourself.
Yeah, very good afternoon to one and all present here. I'm Souvik and I'm from NIT Jamshedpur. I'm a PhD scholar. Sir, we carry out the research that is basically TR1, technology, TRL1 to TRL3. But the CSIR, it is the last three, 7, 8, 9. But most of the time we spend is on the basic research. I wish that how CSIR can reach to us, that is the research scholars, give us a problem, because as ma'am, Dr. Pant, she said, that problems can be from us, but we can, without any experience, we can't pose a problem, because we can say that we can throw a wire to a cloud and we can gain the electricity. That shouldn't be. Rather, if the idea comes from CSIR, and then we can contribute from our side the solution in better way. Thank you.
Maybe you would like to respond?
See, the thing is that I understand what you are saying, that if you are working at TRL 1 or 2 and CSIR is working at 7, 8, 9, how do you bridge the gap, right? But this coming of ideas has to be collaborative, because if you don't think of how do I bridge this gap, then you're just implementing. And that's not the training that you want. You want the training of problem solving, that this gap has to be bridged. Of course, it will be in consultation. But it cannot be that CSIR scientists will come up with a to-do list and PhD student will implement. That's not going to take you very far. The training has to be to think. That comes from doing, from challenging yourself. So that's my...
Hope you got the message. What Madam is trying to advocate is the creativity and serendipity of the problems are the two very important issues. So the problem has to be creative. Need not be always the routine kind of a problem. Any other questions? If nobody is raising the hand, then I will ask the people to stand up and ask the question.
मेरा नाम काजल कुमारी है. जैसे कि मैं अभी का जो जनरेशन है, हम लोग एमएससी करते हैं तो हमसे कोई सीनियर्स पूछते हैं कि एमएससी के बाद आप क्या करोगे, तो यदि मैं अपना पर्सनल बोलूँ तो बोलते हैं कि आई डोंट नो, मुझे नहीं पता. तो कोई कहीं से सजेशन आता है पीएचडी कर लो, अच्छे पोस्ट पे जाएंगे. तो अभी का जो जनरेशन चल रहा है, तो हम लोग देखते हैं कि हमारा जो जॉब का माइंड है कि हमें एक गवर्नमेंट जॉब मिलेगा या फिर हम एक अच्छे पोस्ट पे जाएंगे, इतना एजुकेशन लेने के बाद भी ये कंफर्मेशन नहीं है. तो हम एनएमएल से ये रिक्वेस्ट करेंगे कि वो हमें एक ऐसा एजुकेशन दे जहाँ पे एजुकेशन के साथ एमएससी के साथ हम अपने फ्यूचर को लेकर टेंस ना रहे कि हम अच्छे पोस्ट पे जाएंगे कि नहीं जाएंगे। ये हमारा मन में हमेशा क्वेश्चन रहता है कि एमएससी के बाद क्या करेंगे, पीएचडी के बाद क्या करेंगे, नेट क्वालिफाइड करेंगे, देन क्या क्या क्या।
सो एमएससी का बाद क्या करेंगे, प्रोफेसर मन्ना?
पहले तो हम कोशिश करेंगे समझने के लिए कि आप क्या पूछना चाह रहे थे। मेरा लगा कि आप यही खोज रहे कि एमएससी करके आगे में हम क्या करेंगे, तो या पीएचडी करके क्या करेंगे। आप आगे बढ़ना चाहेंगे, आपके जो ख्वाहिश है वो आप आगे बढ़ना चाहेंगे लाइफ में। तो इसके लिए सवाल ये उठता है कि आप एमएससी क्यों कर रहे हैं, एमए क्यों नहीं कर रहे, या बीएससी करके फिर आगे क्यों आगे आए। हमारे अगर एम ये है कि हम ऊपर जाना चाहेंगे तो उसके लिए हमको इंग्रेडिएंट्स चाहिए, इनपुट चाहिए, ताकि हम प्रॉब्लम सॉल्व करने में या करियर एडवांसमेंट के लिए अपने आप को और काबिल बनाए। ये काबिल बनाने के लिए आपको कुछ ट्रेनिंग की ज़रूरत होते हैं, चाहे वो स्किल हो या प्रॉब्लम सॉल्विंग कैपेसिटी हो या इंफॉर्मेशन हो, ट्रेनिंग हो, जो भी है। मतलब यू वांट टू इक्विप योरसेल्फ टू सॉल्व और टू रीच टू अ हायर लेवल। तो उसके लिए कभी डिग्री की ज़रूरत होते हैं, कभी ट्रेनिंग की ज़रूरत होते हैं, कभी सिर्फ एक्सपीरियंस की ज़रूरत होते हैं, कोई बिना डिग्री। तो ऊपर या आपके जो फाइनल डेस्टिनेशन पहुंचने के लिए कई रास्ते हो सकते हैं, तो आपने उनमें से एक रास्ता चुन लिए हैं। तो अब जब तक उसमें आप हैं, जब तक आप डिग्री कर रहे हैं, तो सबसे अच्छा डिग्री करिए, सबसे अच्छा ट्रेनिंग, सबसे अच्छा कॉन्फिडेंस लेवल बिल्डअप करना, ये सब करिए। आगे में क्या होगा, वो लाइफ ऐसा है कि लाइफ एक तरीके से हम कोई बता सकते कि कोई ऐसा एक क्वेश्चन है जो जिसका आंसर एंड ऑफ द बुक में नहीं लिखा गया है। कहीं भी आप जो चीज़ सोच रहे कि यही मेरा फाइनल डेस्टिनेशन है, हो सकता है कि उससे कहीं अच्छा, कहीं आगे आप बढ़ सकते हैं, या तो कहीं दूसरे जगह भी पहुंच सकते हैं। तो अभी एमएससी हो या बीएससी हो या पीएचडी हो, आप जिसमें अभी शामिल हैं उसको आप सबसे अच्छा परस्यू करिए, सबसे अच्छे तरीके से परस्यू करिए। बी ऑलवेज लुक फॉर एन अपॉर्चुनिटी, एंड कहाँ से क्या अपॉर्चुनिटी आपके सामने आ सकते हैं ये किसी को पता नहीं है। आपको ये भी खुद को पूछना है कि हम अगर एमएससी नहीं करते तो क्या करते। कम से कम घर में बैठ के कुछ नहीं कर रहा हूँ, कुछ सीख नहीं रहा हूँ, इससे तो कहीं अच्छा है कि हम कुछ सीखने के लिए कोशिश। ये एक ट्रेनिंग है, हाँ, ये एक ट्रेनिंग है। इसको आप जब समाप्त करेंगे तब आपको खुद को लगेगा कि आप यू आर नाउ मच मोर कॉम्पिटेंट टू परस्यू समथिंग देन व्हाट यू वेयर बिफोर। ठीक है?
Satisfied? Yeah, Meeta wanted to say something.
This is absolutely quite a relevant question asked by this girl, because since we are running skill development program and it is हिंदी में बोलना है, okay, I got it. तो ये जो क्वेश्चन है ये बहुत ही रेलिवेंट क्वेश्चन है, और हम लोग को ये आंसर देना पड़ता है। जो हम लोग एनएमएल में स्किल डेवलपमेंट प्रोग्राम रन करते हैं, इधर में ये जो क्वेश्चन है हम लोग को देना पड़ता है। उसको बोलते हैं ये स्किल करने का बाद जो पार्टिसिपेंट स्किलिंग किया है उसको क्या जॉब मिला है और वो बिजनेस शुरू किया है। अभी ये देश में एक बहुत अच्छा इम्पॉर्टेंट चीज़ जो हो रहा है, ये जॉब का साथ साथ खुद का जॉब बनाना, जो खुद कुछ करना जो कि आप आपका इनकम कर सकते हो। ये कैसे कर सकते हो? आपको इनोवेटिव प्रोडक्ट डेवलपमेंट करना पड़ेगा। तो आप कैसे सीखोगे? आप साइंस किए हैं, साइंस का बाद आप साइंस से टेक्नोलॉजी जाने के लिए वो जो तरीका है, वो जो माइंड सेट है, वो ट्रेनिंग अभी हम लोग एनएमएल में दे रहे हैं। हम लोगों को एक ट्रेनिंग प्रोग्राम है जिसका नाम है एंटरप्रेन्योरशिप डेवलपमेंट बाय थ्रू प्रोटोटाइप प्रोडक्ट डेवलपमेंट प्रोसेस। तो आपको जैसे हम लोग के इधर में वर्कशॉप है, हम लोग को इधर में बहुत सारा फैसिलिटी है, जो फैसिलिटी लेके पूरा एक प्रोडक्ट बनाओ, सीखो कैसे प्रोडक्ट बनाना पड़ता है, कैसे प्रोडक्ट को मार्केट में सेल करना पड़ता है। ऐसे हम बोल सकते हैं आप पढ़ाई किए हैं इसका माने नहीं है आपको इमीडिएटली जॉब मिलेगा। सिचुएशन इज़ नॉट सो ब्राइट। ओके, आइदर आपको जॉब क्रिएट करना है और आपको जॉब लेना है। तो जब जब जॉब नहीं मिलेगा तो जॉब क्रिएट करो। तो वो ट्रेनिंग एनएमएल में आपको साइंस का साथ साथ वो ट्रेनिंग भी हम लोग एनएमएल में देते हैं। आई अंडरस्टैंड वी हैव टू इंक्लूड करियर काउंसलिंग इन आवर स्किल डेवलपमेंट प्रोग्राम। सो आप लोगों को जो डाउट है, जो आप साइंस का बाद, आप एमएससी का बाद, बीएससी का बाद आप क्या करोगे, उसका जो करियर काउंसलिंग जो है, करियर में कैसे जा सकते हो, उस टाइप का एक सेशन हम लोग इंक्लूड करेंगे हम लोगों को स्किल डेवलपमेंट का प्रोग्राम का अंदर। तो इसमें आई एम श्योर इट इज़ गोइंग टू बी वेरी मच बेनिफिशियल फॉर यू। थैंक यू।
Thank you, Meeta. So the larger message is education is not only about study, it is about experiential learning. So NML उसके लिए बहुत सारा opportunities create करता है. You are welcome to join our skill development programs and get the experience of the various product development and prototype development. और कुछ question?
Introduce. Sir, myself Aman Kumar. I am from NIT Jamshedpur, final year metallurgical student. So, sir, I want to ask a question that now India is producing almost 120 to 130 million ton steel per annum. So, the demand of steel is almost 250 million ton per annum. And in one of the slide I have seen that around 2047 we will produce majorly 400 million ton per annum. But now China is producing 900 to 1000 million ton per annum. So the gap between the India's largest manufacturer of the steel and the second largest manufacturer of the steel, India. So the gap is very, very large. So India is a country having lots of the natural resources, iron ore, coking coal, not a good quality of coking coal. So mainly we are using Dhanbad coking coal and blend with the Australian coking coal to make the coking coal. But lots of the practice in the industries such as industry which are equipped with gas-based steel making, mid-range.
आपका question क्या है? Keep your question short.
My main question is why India is lagging behind the steel production.
I don't know whether it is a relevant question for the topic, but
no, I think what he was trying to ask is that it hurts our pride to hear that China produces 800 million ton and we are producing only 120 million ton. Of course, India can expand its capacity, produce more steel, but what you have to understand is, like, for example, your demand is 100 car per month. Why would you produce 1000 car per month? So if India cannot consume more steel, there's no point producing more steel. What the data that probably you're referring to is that India until now uses about 120, 130 kg per annum per person. That's the consumption rate. The consumption rate, world average is 233 kg per person per annum. So that's almost twice the amount of our consumption capacity. Now imagine, this is the world average. India is 20% of the world's population. And if the consumption in India is equal to the world average, then today you are producing 120 million ton. Tomorrow you'll definitely need 250 or even more amount of steel. So unless there is a major market demand, producing more alone is not going to solve anything. You'll only have lot of shelf value. So the country has to have a major developmental program in terms of creating new buildings, new roads, bridges, lot of civil infrastructure. And as a result, the steel consumption will automatically increase. If the steel consumption increases, there'll be more job creation, more employment generation. Economy will get a further boost. So per capita income will improve. But what I was trying to say is that nothing comes without any challenge. the flip side of that, if you start producing more steel, you'll also start producing more carbon dioxide. So you'll have to have a solution for that. So engineering is not about just pursuing our target in one single possible way. There are many pros and cons of the same target. I hope I could make some sense to you.
Thank you,
Can we
Professor
extend
Manna.
the question to faculties? They are asking.
Yeah, faculty, please.
Yeah, thank you. Myself, Dr. Ranjit Khan from Jamshedpur Cooperative College, Department of Physics. And of course, Sage, my student, he has asked a very relevant question. So in continuation to that, as the topic mentioned that how NML could contribute to the nearby scientific progress. So what, on the basis of my experience, suppose in Delhi, some Nobel laureate has the lecture at IIT Delhi, then the notice is being circulated to the nearby other institution also, like JNU, then Delhi University, and all those who are the talk of relevant discipline, faculty members, students, scholars may attend this lecture. So this sort of thing may be implemented at NML also, that whenever some invited speaker, some relevant speaker which is interested of basic scientific discipline also, then nearby colleges, nearby institution, the similar notice should go, and those who are interested may attend the lecture only, without any other logistic things. So that can be done to the first, that even in one day if a student got so much triggered by the scientific motivation, then if this will continue, then of course this will be better for the nearby places. Then another important thing I would like to say that we have the PG courses as well as UG courses. In the MSc Physics, we have condensed matter physics theory, condensed matter physics and lab. But of course, it is well known that in the state universities, it is very difficult to make the lab, to develop the lab. We don't have adequate funding. But as a talent level, our students every year qualify national level examination, NET, GATE and all. So if some sort of sandwich sort of thing could be provided or not. Suppose in the condensed matter, we are teaching them the XRD, X-ray material synthesis, material characterization. So if they study the theory there, and if possible, then the lab visit may be conducted in collaboration with this. So the theory plus experiment, student will get the exposure of that. So that is possible. And another thing is, we are the shortage of faculty members also. So only hardly 10% or 25% faculty members are there in science discipline. So if possible, then some course or some unit of the course, 4-credit course, if some faculty member from here may take the classes of that unit, so it will be the sandwich program sort of thing. That is the second. One more question I have, so that is the last one.
I will forget your questions actually. So let me answer first your 3 questions.
This is the suggestion.
Okay.
Suggestion that is it possible that whenever some invited talk is being conducted here at NML, then the notice should be circulated to the nearby college. This is the first thing.
I think your first and last is more or similar. That notice should be circulated.
Yeah,
they should be informed well before.
If it is of a generic lecture, we can definitely do it.
Well,
if it is going to be subject specific,
yeah, highly technical is not required, but okay. In general, if
we will do that.
Yeah, well before in time.
Yeah.
You should go so that they should accommodate their calendar also. Yeah. Second thing regarding the theory and experimental, you are talking. CSIR as a whole also has got this CSIR Skill Initiative Development Program. And on every CSIR website, not only NML, there are courses starting from, I believe, from 15 days, 1 month, 2 months, 3 months, where your student can enroll. And then they can come here, do the experiments. So the theory and experiment gap you can fulfill.
Is it during the summer vacation?
It's a rolling thing. Like anytime
then it will be
they
difficult
can
for
register.
us to accommodate.
They can register and they can decide with the faculty of the CSIR lab, NML lab, mutually convenient dates and time they can decide, and they can come. So I'm sure summer rush will be more.
Yes.
So definitely CSIR NML scientists will welcome them. So that program is there. In addition to that, also, I mean, project reports, thesis reports, internship, all those options are there where they can learn the experimental part during doing that courses. So then what was the third question?
Third question is the project work, master's dissertation thesis they have in the third semester and fourth semester. So joint project guidance is supervision.
Dissertation is always
Uh,
offered.
we are always offering.
Yeah.
Of course, due to the limitation of the,
Yeah.
the scientific strength,
Yes.
we cannot accommodate every student,
Yes.
but we accommodate most of the requests. This
Normally
have been
we
doing-
try to accommodate the students.
Yes.
I mean, I think up to 80 to 90% students we try to accommodate. So that should not be any problem. If you still face any problem, you can inform to authorities and we will take care.
Okay, it will be great help for the students.
Yeah,
Thank you.
Any other question? Yes, please.
Good afternoon, everyone. So my name is Ritik, and I am from Karim City College pursuing my graduation in physics. So today, whether it be the faculty members or the panelists, even the individuals here, the common thing that I heard about was for the demand for youngest minds, right? So firstly, we have to know about that. We have only 5 to 10% of the students from the tier 1 colleges, right? And the basic need of a student is great facility of education and also practical approaches, right? But in India, if we see, we have the majority of students from tier 2 and tier 3 cities studying in those colleges where we lack opportunities, right? So the gap between the tier 1 college and a tier 3 college is vast enough, and we cannot bridge that gap in a period of short duration of time. So what I think is if NML can achieve a hybrid centers in different cities where, say it is Jamshedpur, where we can accumulate the scientific minds from tier 3 colleges, as we have some students who can at least have some approach in this sector. But we lack this facility. So most of the students don't get the rightful opportunity which we need. One more thing that I want to add is that in foreign countries, there is no concept of tier 1 colleges and tier 2 colleges or tier 3 colleges, right? We have the same facilities in each and every colleges, and the research mind is more probable in those countries. Therefore, the development that those countries are gaining is more rapid than in India. So to encourage the young generation, we need to focus more on the tier 2 cities or tier 3 cities, and yeah, that's all. Thank you.
So basically, the first question is the NML should put in more learning centers, sort of a learning centers, and the second two is there should not be any discrimination between the different tiers of educational institute. Is that your question?
See, depending on the strength of the lab also and the facilities which we have, we try to cater best in various forms. Like a skill development program is there. Virtual lab concept has come up, which is very useful. I mean, at a time you can reach to thousands of people, thousands of students. Only thing at the other side, you should have the connectivity. So that we are trying to fill up these gaps. At same time, we also expect efforts from the institutes, the other side, that they try to have the minimum facility which can cater the students on day-to-day basis. For the specialized things, definitely we are here. And as and when you approach, we welcome you to our lab. This is what I can tell you.
So Manna, would you like to add anything? Yeah, please.
See, I think it is not correct to say that other countries don't have tier 1 and tier 2 and so on. This differentiation exists all over the world. Whether you take the US or you take Europe, there are well-known well endowed institutions, and then there are not so well known and not so well endowed institutions. We of course have this additional, people now call it the demographic dividend, but it is still a challenge that we have a huge population of young people who are aspirational, and there is there's a strata of institutes, right? There are better institutes and not so good institutes, and I don't think anything we discuss in this room is going to do away with that. Certainly not in my lifetime. So I think that is a fact. What we are discussing here, and I'm really impressed to hear of the initiatives that NML is taking, is that, okay, given this, how do other institutions, because I don't think education, I don't think that is the primary mandate of NML. That they're doing it is remarkable. So let us discuss means of reducing that disparity without saying that, oh, it exists only here, it doesn't exist elsewhere and so on. It exists everywhere.
Yeah, please.
Thank you, sir. Sir, one thing. Is it possible, can we share the library facilities? Because Tier 2, Tier 3 colleges, for research, it is very important. Library in the sense, of course, the books, the basics books, all colleges they have. But the journals, they are very costly, and it is not at all affordable for all the colleges. And that is the bottleneck for all the colleges for the research. So, thank you from all the colleges that yes sir, these are the basic questions students are asking. These are the fundamental questions, because Tier 2, Tier 3 colleges students, they are facing it. And the NML, whatever it is giving, I understand it is not the prime job to help students directly. You have other jobs also. The main job is your research and all. But side by side, if you are helping to society, it is really good. So tell something about the library facilities. If it is possible, it would be a very great for all the students of Jamshedpur.
See, HR development, basically, it all comes under the umbrella of HR development. It is initiated in a big way in CSIR as a whole. And if you see before even ACSIR and after ACSIR, it has made a remarkable change. At present, we have around 5,000 ongoing PhD students across country in 37 CSIR labs. So we are trying to do our best in that way. Coming to your other point, library facility, now most of the journals are now on internet. The books, definitely, we still have probably the richer library than many other institutes in and around Jamshedpur. So students can definitely come through proper channel and use that. They are always welcome. We want they should come and utilize our library. And the journals, definitely, they have to get connected with some of our faculties, and through them they can definitely utilize that facility also.
Yeah.
Okay? Thank you.
Are there any more questions?
Any questions from students? Any questions? Hindi?
Yeah.
Let me respond to one of the young fellows here, what he asked about. See, no two individual is the same, can never be the same. We carry the same number of chromosomes, but eventually we cannot be exactly identical. Similarly, life never gives you the same opportunity to every individual in a community. There is always a variation. So if you, for example, if you have a class of 100, there will be only one first in any given test. Now, that doesn't mean that only the first or the second is going to get all the opportunities in life, and the 100th one will essentially be left with no option or no choice. That's not true. For one single reason. While life doesn't offer the same opportunity, life doesn't give you the opportunities to the same person forever. The person who is topper, the first today, if the same exam is administered tomorrow, there's no guarantee the same person will emerge again the topper. There's no guarantee. There's also no guarantee the one who is 100th will always remain 100th. There's also equally possible that the ones who are not doing well today will do much better tomorrow and even emerge as topper in some other trait of life. So, like one of our young lady was raising a point, why am I doing MSc? What is ahead of me? We essentially all would like to equip ourselves for life and the greater challenge of life. So today I have certain options. I'm born in this country. I'm going to the school in Jamshedpur, or I'm pursuing physics or chemistry or mechanical or for my discipline. So this is the limit of the opportunity to me at the moment. And I should make the best use of it. Because if I don't do that, and if I keep lamenting, why am I studying mechanical and not electrical, or why am I doing MSc and not MTech, then we are essentially wasting the opportunity given to me. Whatever I have an access to at the moment, at this stage of my life, I should derive the best possible benefit out of that and prepare for even greater challenge and opportunity in the future, both challenge and opportunity. I don't know what lies ahead. Something may crop up. So whenever I go to the next level, whether it's a job in private or government, or whether I'm having a salaried job or I've created my own enterprise, I basically should be able to perform to the extent desired. So I should be able to answer or solve the problem posed to me. So this is how we all grow. Whatever comes in our way, we try to learn from that and make ourselves better equipped, more competent for the future. That's how we should proceed. And about tier 1 and tier 2 or tier 3, this is a natural consequence. You know, if you have 100 rupees, you would like to buy the best of the products available in the market, which should last forever, which should be the most beautiful thing in the world. Everybody wants something like that. So there'll be an automatic gradation. So some are better equipped, but they also earn some of their reputation, some of their status in the society. They earn and they have to maintain. It's a very competitive world. Every institution, every individual, every department, subject domain, every company, commercial entity, always are under huge competition. So we have to constantly perform and outperform others. That's how in life always the better species evolve and sustain. So that's the training of life. Okay.
Thank you, Professor Manna. I think a last point, because we have to wind up this event. We should have been wind up by 3:30. We are 10 minutes late.
Yeah, I just want to make a point here quickly. That is the tier 1, 2, 3. From where it has come, I don't know. But if somebody thinks that I am in tier 3, please don't think so. Because unless you think that you are the best, you can never be the best. Okay? That is point number 1. And the second thing is that I like to say is that this internship is very much important. Okay? I'm from ISIR. Of course, the ISIR system, the students, they start going to the laboratories from their 3rd year. I'm talking about the 5-year integrated, this masters. So that means they're BSc final year, they start going to the labs. And so they know what a lab is, they know what is a research. So when they go for the final research for their the PhD, they are much more ahead as compared to all the universities. Having said that, there are a lot of applications which come to us for doing an internship. Okay, not only for the summer internship, but also for a 6-month internship. I think all of you who want to take up the engineering or science in the future, you must think about applying internship to multiple places. I'm not talking about the CSIR labs only. I'm talking about every other research institution or the university where there is a lab. You write to them. Somewhere, some faculty, the professor might say yes to you, and that will be a very good opportunity. So please, don't stop, and please explore yourself. Yeah, that's what I want to say. Thank you.
Thank you, Professor Sayan. I know that you will be having many more questions, but due to paucity of the time, I have to wind up here. And I thank the panelists for their excellent responses. And with that, I would like to hand over the stage to Mandal.
Thank you, Dr. Sivaprasad, for nicely conducting this session and making this session more interactive. Thank you to our esteemed panelists for sharing your expertise and insights with us. We had a thought-provoking and informative discussion on very relevant topic to all of us. I hope that everyone in the audience has gained new ideas and perspectives to take away from today's event. We certainly look forward to similar types of interaction in near future. Based on today's discussion and based on the concluding remarks made by our chief guest during his inaugural talk, it is clearly understood that challenges are enormous, which needs to be addressed. But there are many hopes. If we look at the average age of India, it is below 30 years, where the rest of the world are actually aging, where the average age in the rest of the world is above 40. So therefore, if we equip the young minds, educate them well, and train them well, so that we can develop well-formed minds, then one day we can say to the rest of the world that we are coming with a lot of innovations. So with this, now on behalf of CSIR-NML, I will request our director to present a memento to all the panelists as a token of our delight and respect. And I will also request Dr. Sanjay Kumar to please join us on the stage, on the dais. Thank you, sir. As a part of the academia meet, we also organized the poster competition for the students on a specialized theme, that is metals and materials for growth of nation. I must convey that most of the posters are very much relevant to topic and highly rich in technical content. A big congratulations to all of you who have prepared their poster in a very short notice. All the posters are judged based on the technical contents relevant to theme and some other criteria. And I will formally announce the results of poster competition and request Professor Indranil Manda to hand over the certificate and prize to the winners. So, the third best poster award goes to Samarjit Kumar from NIT Jamshedpur. So this is actually the first award. No, it's fine. He's the first. Okay. Okay. So they made the correction. Actually, I make the mistakes. Now the second best award goes to this. This is the first prize. I make the mistakes. Now the second best award goes to Aman Kumar from NIT Jamshedpur again. And third prize goes to Minal Kanti Jha from Cooperative College, Jamshedpur. So please take seats. So congratulations to all the winners. We have come to an end to this program. Before we wrap up, I would like to take this opportunity to show gratitude and hearty thanks to our esteemed panelists for providing their insightful remarks. Thank you, panel member, for making this event possible. I am certain that the takeaways from these interactions will further deepen our thinking and find out the right direction for future actions. I hope the event has been very effective in meeting its purpose. We are thankful to Dr. Avanish Kumar Srivastava, our director, for gracing this occasion and providing his constant encouragement and logistic support. I, on behalf of the organizing committee and on my own behalf, like to extend our thanks to all the delegates and dignitaries for coming to CSIR-NML. I thank all the participants and audience, mainly faculty members, teachers and students. The event could not have been success without your enthusiastic participations and engagement. I am sure that you must have many questions or queries, so please feel free to write us. I will be failing in my duty if I do not convey my thanks to Dr. S.K. Tiwari, the DRESS convener, Dr. Raghuveer Singh, the coordinator of this event, Dr. S. Sivaprasad, the moderator, Dr. B.C. Srivastav, and many more for their tireless effort throughout the preparation of this event and to ensure that the event is successful. I acknowledge the unwavering support received from all the members of the organizing committee, and all the supporting staffs of CSIR-NML in general. My thanks are due to each and everyone for giving their valuable time for organizing this event. Thank you once again for joining us today. Thank you all.
Requesting all of you to please be seated. The valedictory function is going to start. सब लोग प्लीज़ बैठे रहिए, कोई हॉल छोड़ के मत जाइए. वैलिडेटरी फंक्शन स्टार्ट होने वाला है.
वो तो तुलसी हाँ देखो बोल दिया आ जाओ अंदर आ जाओ गिलास सब चेंज कर दिया ना गिलास सब चेंज कर दिया था गिलास का पानी रोक कर रखा नया नया गिलास हाँ घटा देते हैं
बुरा लग रहा है 6 खुला रहता ना एक खाली रहता अच्छा नहीं लगता बिना
Participants' certificates are being distributed at the registration counter. You may collect from there. What? Okay, it will be distributed after the program.
इसको तुलसी इसको निकालो ना इसको निकालो किसका प्रेजेंटेशन दिखाने का देखो कल प्रेजेंटेशन से बनाया हम बोले थे
इसको फिर खाना पड़ेगा थोड़ा देर बाद
बोले थे
इसको हटाओ पकड़ना वो तो पास है वो तो जा रहा है तुम्हारा ऑनलाइन चलते नहीं चंदा किया था ना? कहाँ गया? गिलास चेंज किया था ना? गिलास को चेंज किया था? रोके रखा ना? नहीं इसी पर बोले भी तो ये इसको सीधा करना होगा। यूज किया ही नहीं, यूज नहीं किया।
चॉकलेट्स और भर दीजिए।
वो शायद चॉकलेट खत्म हो गई।
There is no.
हटा दिए।
अच्छा कोई बात नहीं, बोलना निकाल देंगे।
All of you are requested to kindly take your seats. We are about to start the valedictory function in a moment. Thank you. किसी और को भेज के रखना, सबको ज़रूरत है फोटोग्राफ, तो सबका फोटोग्राफ तो इस फोटोग्राफ तो वैलिडिटी के बाद बहुत होने वाला है। नहीं हो तो क्योंकि वो मैं गारंटी नहीं दे सकती, अभी शुरू होने वाला है फंक्शन, तो पेमेंट तो उसके थोड़े देर टाइम के बाद होगा, पेमेंट तो थोड़े टाइम के बाद होगा। तुम फटाफट जाओ ताकि होके चलो। Just as in the beginning of the program, a kind request to all of you to kindly put your cell phones on the vibratory mode. We'll start the program right away as soon as the chief guest arrives. Thank you. Again, I'm requesting all of you to please take your seats, those who are standing at the back. May I request all of you, those who are standing outside the auditorium in the foyer area, to please come in and take your seat. Our chief guest has arrived. Please take your seat. We'll start the program in a moment. Thank you very much. First, the safety announcements. We have two exits in this auditorium. One is right at the back, and one is to your right-hand side. To my right-hand side, I'm very sorry. And you can see that the door which leads to the back of the auditorium where you can escape from. So there are two exit gates, and other than that, I would like to start with the general welcome of the valedictory session. Ladies and gentlemen, I take this opportunity to welcome each one of you to the valedictory function of 1 week, 1 lab, which was held in CSIR-NML from 24th to 28th April. The active participation of everyone, let me emphasize the word everyone here, affirms the relevance and meaningfulness of this celebration. It demonstrated the term teamwork in its true sense. In fact, from Monday, I think most of you will feel a certain emptiness. With this, I would like to request all the dignitaries who are here with us today, Professor Indranil Manna, who is the Research Council Chairman and CSIR-NML Vice Chancellor, Birla Institute of Technology, BIT Meshra, Ranchi, Jharkhand, and who is the chief guest of the ceremony today, Dr. Avnish Kumar Srivastav, Director CSIR-NML, Dr. S.K. Pal, Chief Scientist and Head Research Planning and Business Development, CSIR-NML, Convener of the CSIR-NML 1 Week, 1 Lab program, and Dr. Sharmishta Sagar, Chief Scientist, CSIR-NML. I would like to request all of you to please come up on the dais and take your seat. Thank you very much. Thanks, all of you. We'll start the program by the presentation by Dr. S.K. Pal on the way forward from CSIR-NML 1 Week, 1 Lab program. Dr. S.K. Pal, we would like to hear from you. Thank you.
Respected Chairman, Research Council, Director NML, Dr. Sharmishta, my dear colleagues and friends. So we are now almost reached at the end of our campaign, 1 week, 1 lab programs. So in this total, my job is to summarize whatever that we have learned, what is the takeaway, and what is the way forward for what are that programs we have conducted. 1 week, 1 lab campaigns by CSIR is primarily plans to showcase these technological innovations and achievements by organizing various programs, week-long programs like workshop, industry meet, student connect, society connect, display of the technology, and so on. Apart from the above, under the 1 week, 1 lab programs, the laboratories to identify the needs of the regions, industry, and provide suitable solutions for them. During these week-long programs, lab has organized various events as per the format of CSIR, and I just highlights what is the basically takeaway and way forward from that learning of the 1 week, 1 lab campaigns. So we have planned the campaigns not only for showcasing our legacy and achievements, but we have emphasized to strengthen the connectivity between the pillars of the research and innovation ecosystem of NML. Our program has been designed to connect academic institutions, government, industries, startup, MSME, entrepreneurs, innovators, as well as students. To connect the local government, we have planned our programs like inauguration functions to be conducted at Ranchi, and we have done this thing. Keeping in view the participation of the large number of key government officials in the meeting, we are quite fortunate to have Honorable Governor Jharkhand as well as head of our family DGCSR in curtain raiser events. Honorable Governor has kindly appreciated NML's participations, involvement in government mission programs like Skill India, Make in India, Swachh Bharat, Atmanirbhar Bharat, and so on. He emphasized that NML should play a very important role in developing mineral-rich Jharkhand, and in this regard, Honorable Government has kindly shown his interest to visit NML. To connect with the industries, the laboratories organizes two important workshops, one is on rare earth metals and other on hydrogen storage and transportations. A large number of industry participation we have just seen in these two workshops, and they have delivered the talk. The purpose of the workshop is to strengthen our research network in rare earth, as well as to develop a center for excellence to deal material challenges unlocking the hydrogen era. We are quite successful in achieving our goals. Towards strengthening the industrial relationship with Tata Steel, we have organized Tata NML Interaction Meet as a part of 1 Week, 1 Lab campaign. Existing collaborative models will be revisited for gainful utilizations of R&D outcomes by the Tata Steel. A communication system has planned for identification of the industrial problem and formulation of the new projects. To connect with academic institutions in NML R&D ecosystems, we have organized Academia Meet to strengthen the relations among the college, university, and research organizations, and discussed how NML can play a role to help academia in and around the city and Jharkhand state. We are quite fortunate to have very distinguished academics in this meet. To connect MSME startup entrepreneurs, we have organized a techno-entrepreneurship meet to create a platform where MSMEs, entrepreneurs, startup come together and can explore the technologies ready for commercialization at NMLs. We are quite fortunate to have Secretary Technology Development Board as well as President CII Jharkhand Local Chapter President in this meet. NML will explore to commercialize technologies at TRL 6 and above to the prospective licensees with financial assistance from the Technology Development Board. To connect with these grassroots level entrepreneurs, innovators, the lab has organized a unique Silpokar Mela, that is artisan meet. The objective of the meet was to strengthen MSME ecosystem where artisan, technology provider, government, e-marketing official, export council official will join hand in a single platform. In one hand, the artisan can upgrade their technology with the intervention of the NML knowledge base. On the other hand, they have the opportunity to get guidance how to get better price of their product in the marketplace. In Social Connect, we have organized Jigyasa School Student Scientist Interaction Program where more than 500 students from the different schools participate in these events. They have visited NML, different facilities. We have also organized Technology Challenge Hackathon where the school children of class 8 to 12 participate in the events and make presentation on the theme Quest for Smart and Sustainable Society. CSIR-NML has set up an exhibition for showcasing its technological innovation and inventions. The exhibition is housing more than 80 number of technical posters covering various domains of these S&T contributions. In addition to the technical poster, the demonstration of the technologies, inventions and model was part of the show. A set of futuristic idea by the young scientists also presented in these exhibitions. We have a very successful 1 Week, 1 Lab programs, and as a coordinator, I like to acknowledge the untiring efforts of many of the coordinators and team members for success of 1 Week, 1 Lab programs of NML. Thank you.
Thank you very much, Dr. Pal, and for all the hard work you did to make this 1 week, 1 lab program a success. I would now request our director, Dr. Avnish Srivastava, to kindly deliver the speech and say a few words about closing of the program. Thanks.
Good afternoon. Welcome to the validity session of this 1 week, 1 lab program. The program itself was long awaited, 1 week, 1 lab, in the sense that, as our chief guest also mentioned, and it is that CSIR was established in 1942, and in 2023, more than after 80 years, first time CSIR has come out with this kind of unique idea of having 1 week, 1 lab program to showcase our strength in the form of innovative ideas, knowledge, and technological breakthroughs to the common man, students, industrialists, entrepreneurs, and whoever is directly or indirectly related with science and technology and wants to carry out away the science and technology in future. Dr. Paul has made a very kind of a very good summary of the program, what we had. So I don't have much to say. Only thing I want to say that this program, we tried to encompass various activities, starting with inauguration, then workshop on rare earths for self-reliant India, then exhibition, and Jigyasa for school student, teachers, and scientist interaction, then technology challenge hackathon, workshop on materials challenges in unlocking the hydrogen era, and then futuristic ideas in the form of posters by young scientists, industry and entrepreneur meet, Shilpkar Mela, and today morning we had academia meet, and in Chennai Center we had industry meet, CSIR-NML's Chennai Center we had industry meet. So overall we tried to cover all the aspects, and we strongly hope and believe that this is going to be a very, very useful for the country and for every individual in the coming future, this kind of program. One more thing which I wanted to highlight, and fortunately Dr. Pal probably missed, that in the beginning itself, I believe second day, there are some posters still people can go and see the futuristic ideas presented in 1 week, 1 lab in the form of posters, and various ideas are there. First is empowering rural communities with green hydrogen production, a village level approach, residual stress determination by contour method, liberation of metal clads of WPCBs through chemical pre-treatment, then waste to wealth process for production of chromic oxide from chromite beneficent plant, telling future of metal extraction from lean grade ore through electrokinetic in situ leaching, rapid alloy development through integrated R&D assembly line concept, then machine learning for mineral liberation studies and particle morphology analysis, then solar steel, then green, this non-destructive evaluation solutions using eddy current technologies, and functionally graded materials by additive manufacturing, green steel from copper smelter slag, creep properties evaluation by indentation of small specimen, increasing temperature capabilities of nickel-based superalloys, and design of ultra-high entropy catalysts for electrochemical water splitting, advanced reactive molecular dynamics simulation, and many more. So this is the future ideas, thrown in the public where anybody and everybody is welcome to come and interact with CSIR-NML staff, scientists, and technical both. And we can try to work out, because I am sure these futuristic ideas are going to be very, very useful for mankind and for the country and globally too. So with this brief note, I can understand and I can feel that how we are celebrating validatory program of 1 week, 1 lab, which was quite awaited, long awaited. And today, on 5th day, we are in the this concluding session of this program. And I again say that it is going to be very useful. And we are really fortunate to have this kind of gathering on this concluding session. And then in particular, our own Research Council Chair, Professor Manna, who has started from early morning, and since till now he is very active with us, and he is attending all the program since morning. So we really thank you, sir, for your gracious presence on the validity session of this program. And without you, probably we could have missed something, but it is really great that you are with us. So with this brief note, once again, I welcome to this validity session, which is going to be concluded very soon. Thank you very much.
Thank you very much, Dr. Srivastava, for bringing out, for re-emphasizing, in fact, again, the versatility of the OWL program which we had, and definitely your support mattered a lot throughout. I would like to request the authorities to screen the capsule video which we prepared during the program for all of you. Thank you.
Metallurgy, the art and science of making and using metals, has contributed enormously to the growth of human civilization. India, with a metallurgical heritage of over 7,000 years, has been the leader. In 1942, when India was at the dawn of its freedom movement, Sri Shanti Swarup Bhatnagar, the visionary leader, realized the importance of metallurgy in shaping the growth of independent India and decided to establish the National Metallurgical Laboratory, one of the first 5 laboratories of the Council of Scientific and Industrial Research. After 8 years, Prime Minister Jawaharlal Nehru inaugurated the National Metallurgical Laboratory, popularly known as NML, on November 26, 1950 at Jamshedpur. The mandate was to bring out the treasures of our soil to the surface, cast them to shape and put India in the path of industrial growth. Under the dynamic leadership of President CSIR, Vice President CSIR, Director General CSIR, and its director, NML is marching ahead to fulfill the dreams of 1 billion Indians.
CSIR National Metallurgical Laboratory, Jamshedpur, is a national laboratory of international repute. The laboratory is engaged in a broad range of research activities in the field of mineral processing, metal extraction and recycling, materials engineering, analytical chemistry, and advanced materials and characterization. When we think of research, we don't only think about creating knowledge, we also think about how the knowledge will actually be transferred to the industry so that it makes people's lives better. Over the past 70 years, industrial collaborations have been the hallmark of NML. More than 100 industries from India and abroad has benefited from NML in various ways. Moreover, the high quality HR development and direct contribution to the society through scientific interventions is an important mission of the laboratory.
Efficient utilization of India's natural resources for the betterment of quality of life has been the motto of NML from its inception. Using pilot plant facilities, NML has developed process flow sheets on beneficiation of iron ore, limestone, coal, bauxite, barite, sillimanite, and lithium ore to improve the productivity. NML's column flotation technology for beneficiation of low-grade ores has set a benchmark in the mineral processing industry. 7 industries across India are now using the column flotation cell to beneficiate the different low-grade ores. Dry beneficiation of coal to save the wastage of water in coal washeries and preparation of metallurgical grade coke using Indian non-coking coals to reduce import of coking coals are some noteworthy contributions. Post-independence, when industrialization was the need of the hour, NML responded by developing technologies to produce pig iron, sponge iron, ferroalloys and magnesium metal that resulted in establishment of a number of industries. NML also developed new alloys like nickel-free stainless steel, PM2 conductor aluminum alloy to replace copper, and aluminum magnesium alloy coins for the Indian Mint. To contribute to the modern India's growth, NML has participated in flagship programs like Atmanirbhar Bharat, Make in India, Startup India, and Skill India. To realize the dream of Atmanirbhar Bharat, NML developed technologies for production of several strategic metals, including tungsten from tungsten carbide scraps, sodium metal from sodium chloride through molten salt electrolysis, and manganese metal from manganese ore through electrolytic route. Technology for production of corrosion-resistant brass ammunition was developed and transferred to the Ordnance Factory Warangal, Maharashtra, to ensure availability of world-class ammunition to India's armed forces. When India embraced the path of rapid development through construction of railways, power plants, bridges, airports, and rockets, NML contributed by certifying the quality of the metallic components at its Crete laboratory, one of the largest in Asia. Indian Railway, Indian Air Force, DRDO, BARC, ISRO, NTPC, and a number of consumer industries all take the help of NML for remaining life assessment and failure analysis. Under the Make in India initiative, NML developed sensors and devices for the metallurgical industry. For the first time in the world, a device to detect the breakout in industrial billet casters was developed using fiber brag gratings as the temperature sensor. The technology won Tata Innovista Award in 2022. FlowGuard, Zincometer, and Maxtrix are some other devices developed and commercialized by NML through private companies. NML is producing and marketing certified reference materials to ensure the quality and global traceability of analytical test results. With 39 number of metallurgical CRNs and NABL accreditation as per ISO 17034, NML has placed itself as a global player in the CRM market. MSME and startups are the backbone of India's economy, and their role is pivotal towards India's goal to become a $5 trillion economy. NML has taken up the task to make the MSMEs globally competitive by providing modern technology and technological guidance. The Urban Ore Recycling Center of NML develops technologies for recycling of e-waste in the environment-friendly and economical manner. It has transferred 10 technologies to the MSMEs, and in recognition, NML has received the CSIR Best Technology Award in 2020. In the Waste to Wealth initiative, NML developed technology to produce paving blocks from fly ash and blast furnace slag using geopolymerization technique. Technology for production of high-quality iron oxide from waste pickle liquor was also developed. This technology has received NRDC National Innovation Award in 2020. At a time when India is celebrating Azadi Ki Amrit Mahotsav and G20 presidency, the world expects India to be a leader in science and technology. NML's research work on galvanization of high-strength steels for automotive applications, self-healing coating for maintenance-free corrosion protection of steel structures, novel catalytic nanomaterials for hydrogen generation through water splitting, production of new alloy powders for 3D printing, and holistic utilization of red mud in partnership with major aluminum industries are targeted in that direction. As a responsible organization, NML has taken up the responsibility to solve the problems of Indian citizens through technological interventions. For the brass artisans, NML has developed a brass melting furnace which not only reduces the melting cost but also protect the artisans from exposure to harmful zinc vapors. NML has also developed an anti-tarnishing lacquer to improve the surface finish and maintain the metallic luster of metal handicrafts.
हम लोग पिछले 5 सालों से NML जमशेदपुर से ये एंटी टार्निशिंग लैकर ले रहे हैं। हमारे यहाँ हम लोग फैशन ज्वेलरी बनाते हैं जो कि स्क्रैप ब्रास से बनती है। जब से हम लोग NML द्वारा बनाया हुआ ये लैकर यूज किया है, हमारी सेलेबिलिटी बहुत इंक्रीज हो गई है।
Under the Skill India initiative, NML runs skill development programs for students and professionals to enhance their employability and performance. Invite school students to visit the lab and get first-hand experience on scientific research, and trains women to upgrade their skills and take up entrepreneurship.
अभी तक माना जाता है कि लड़के ही कारपेंटर के फील्ड में आते हैं, बट मैं इस सोच को बदलना चाहती हूँ कि लड़कियाँ भी इस कारपेंटर के जरिए काम कर सकते हैं और मैं अपने पापा के बिजनेस को कारपेंटर के द्वारा ही आगे बढ़ा सकूँ.
With the state-of-the-art infrastructure and hard-working dynamic group of people, NML is always striving towards becoming a global leader in metallurgical research. To showcase the scientific legacy, unique innovations, and technological advancements to the society, NML is hosting 1 week, 1 lab program during 24th to 28th April 2023. We welcome everyone to visit CSIR-NML and witness our scientific and technological contributions to India's growth and prosperity. Let us celebrate our contributions together. Let us join hands to build a stronger India.
Thank you very much. I would like to move on with the program, and this is the point where I would like to introduce you all to our chief guest today. Professor Manna is a very familiar face to all of us. He is a J.C. Bose Fellow of DST and is currently the Vice Chancellor of BIT Meshra, Ranchi. Okay. I would not go through his academic profile, but I would like to definitely ask him that if he had a fantastic time at the Academia Meet today, and we are privileged to have you with us today, sir. So without taking any more time, I would like to request Dr. Manna to share his thought on the program with all of us.
Dr. Srivastav, Director NML, Dr. Sagar, Dr. Pal, all good things eventually come to an end, so this is also time to wind up. But going by the level of participation and interaction, I think all of you would agree, at least on the last day, we have had a wonderful function, the winding up, the concluding function for the 1 week long celebration of 1 week, one laboratory initiative of CSIR. In the morning, I did mention about the importance of CSIR, the very major contributions made over the years. You just saw a very nice video about various technological interventions made by this laboratory. This laboratory also is very well known for contribution to fundamental science, in particular in the materials engineering area, covering both extraction and processing of solid metals, as well as the physical metallurgy aspects of it, various alloy design and so on. Component integrity evaluation of various types under cyclic load, under elevated temperature. These are also very major contributions of this laboratory. I am sure this laboratory still exists and must be producing good results on fatigue testing and the creep battery. These are two very unique facilities of this laboratory. Our young friends were very keen. They expressed their desire to see the facilities. I certainly would implore upon them to visit these whenever opportunity arises, because we must realize that the laboratory is meant for a particular purpose and they cannot deviate much from their core mandate. Yet they'll be very happy to show you these facilities, some of the way the materials are characterized and tested, and the way new materials are designed. So this certainly would make you more interested in this part of engineering related to development and deployment of solid materials. See, this particular laboratory, for the benefit of the young friends here, is the 5th oldest, if I'm not mistaken. Founded in 1950. So you can imagine a very glorious 73 years of existence, and one of the earliest and the finest. And in metallurgical discipline, this certainly is one of the top 3 laboratories in the country. So it certainly will help you a lot if you can visit some of the facilities and get to know about what are the new developments taking place. It has a long checkered history, and in certain disciplines, there was a time when very many process metallurgy, extractive metallurgy flow sheets were created in this laboratory, and that too in for metals which are not very well studied in the country, something like magnesium and several other such non-ferrous metals. And material evolution is another very strong point. So the whole purpose of this exercise is to reach out to the community, and that has been done in ample measures. So on behalf of all of you here, I would like to compliment CSIR, and in particular all the staff scientists and employees of CSIR-NML for organizing this wonderful event. And I'm sure this laboratory will make many more momentous contributions in years to come. So I wish NML a very glorious future and many more important contributions to the growth of the nation and to the subject domain. I wish my young friends here present very best for their future career endeavors, and all of us put together should make the country more successful and proud. Thank you very much, and Jai Hind.
Thank you very much, sir, for your kind words of appreciation. I would now request our director, Dr. Avnish Srivastav, to kindly present a memento to our chief guest. Thank you. Please. Now I would like to request Dr. Sharmishta Sharu to kindly deliver the vote of thanks to all of us. Thanks.
It has been an incredible few days, but like all good things, 1 week, 1 lab campaign of CSIR-NML comes to an end. Professor Indranil Manna, Vice Chancellor BIT Mestra and Chairman Research Council of CSIR-NML, Dr. Avnish Kumar Srivastav, Director CSIR-NML, Dr. S.K. Pal, Chief Scientist and convener of this 1 week, 1 lab program, invited speakers, students from various colleges, representatives of press and media, my dear colleagues from CSIR-NML, ladies and gentlemen. A very good afternoon to one and all. Today, I feel honored and privileged to have been allowed to propose the vote of thanks on the valedictory session of the week-long program, 1 week, 1 lab of CSIR-NML. We may have had longer programs earlier, but none like this. The scale, the purpose, and the intent have all been unique. To be able to pull off something of this magnitude and impact needed months-long preparation, support from every quarters, and involvement of each and every one in the organization. I'm happy to stand here today to acknowledge all of them. On behalf of CSIR-NML's whole family and on my personal behalf, I sincerely thank Professor Manna for taking time out from his busy schedule to grace our valedictory function of this 1 week, 1 lab campaign. Thank you, sir, for being with us whole day and on this auspicious occasion and blessed us with your insightful thoughts. It shows your affection and love for this lab. Organizing an event of such scale needs an extra effort. A motivated leader and one having a bird's eye view for details. We are fortunate to have such a person as our director, Dr. Avnish Kumar Srivastav. On behalf of the whole organizing committee and CSIR-NML, I thank our director for your valuable advice and minute-to-minute monitoring for flawless execution of the event. Thank you, sir, for your encouragement and for being with us even during the holidays to help us to prepare the roadmap for this 1 week, 1 lab campaign. In this week-long program, we have had with us many renowned personalities from the industry and academia. I'd like to thank all the invited speakers who inspired us with their presence and enlightened us with their knowledge. I also thank all the students and teachers from various schools and colleges, young entrepreneurs, delegates of each day program to be part of this campaign. Without them, this program could not have reached this height. I'd like to thank press and media for the wide coverage of 5 days program. Thank you for covering and making the people of India aware about our own program and these activities. Our sincere thanks is also due to our engineering, janitorial, horticulture, administration, finance, purchase, and especially canteen for their constant support to conduct this event very smoothly. An event of this dimension cannot happen overnight. The wheels start rolling months in advance. We have been fortunate enough to be backed by a very motivated and dedicated team and volunteers. Words are not enough to thank everyone for the involvement they have shown and the willingness they have expressed to take on the completion of tasks beyond their comfort zones. Actually, they all deserve a wide round of applause for their untiring efforts to make the event a memorable one. May I request you all to give a big round of applause for the whole organizing team. Finally, I would like to thank all of you present here with us today. Thank you, one and all. Thank you.
Thank you very much, ma'am. I would now request all of you to kindly stand up on your place for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thanks all of you for being here, for your time, and we have arranged for a high tea just outside the auditorium. Yes. May I request all of you to please assemble on the stage for a group photograph?
Please, all of you can come to the stage for a group photograph. I request all the members of NML family, sir, NML's, and also the students and who are here. Please come. Nobody will come, just whoever is coming, just ask. See, nobody will come. देखो ना कितना आता है. People will not come.
Suppose if everybody has turned up. मैम कुछ आगे खड़े तो लेडीज को आगे चेतन में Thank you. Successfully completed.
अरे दो मोबाइल है उसमें मत ले जाओ.
हाँ फोन कर रहे थे रुको ना थोड़ी देर बाद बात करें कब तक तुम घर जाओगे
उधर कर लो, है ना?
लेकिन आप अभी उधर रिटायरमेंट वाले उसमें रहेंगे तो कैसे भिजवाओगे?
तो भिजवाओ ना, मेरा रूम खुला रहेगा। मैम आप ये कैसे निकल